Community, welcome to the PX4 Developer Summit. I want to thank everyone for tuning in. We're incredibly excited to have more than 1,600 of you here. Before we get started though, I want to thank the team of more than 70 who are making this event possible. Staff, volunteers, speakers, sponsors, partners, and last but not least, my family. There's no denying that COVID-19 has dramatically impacted the lives of all of us. Remember, one small gesture can save lives. Please follow your local authority guidelines, take care, and help others. During the following days, we're going to take a deep dive into the depths of the PX4 community. It's been a year since we last met in Zurich, and the community has been really hard at work. I want to start the day off by announcing that Maxwell Innovations today joined Dronecode as a silver member. Thank you, Maxwell Innovations. I'm going to be hosting the main track of the conference. I'll be joined by community speakers selected by the content committee. You will be able to ask questions to speakers at any time during your presentation. Our team of community volunteers will collect questions. The pre-recorded talks can be found on the PX4 YouTube channel. Make sure you don't miss the speakers on the chat room while the video premieres though. Feel free to ask as many questions as you want. It's a unique opportunity. Make sure you make the most out of it. Make sure you follow PX4 on social media for special announcements. Let's get started with our first speaker. Dr. Lawrence Mayer is the co-founder of Authorian, chairman of Dronecode. He will be presenting Setting the Standards in the Drone Industry for a Decade. Lawrence is calling in from Zurich. Please stand by while I connect you. Don't move. Be right back. Community, this is Ramon speaking. I'm really happy to be here with you today. Dr. Lawrence Mayer is calling in from Zurich right now. Let me connect you right now.
I really hope that we can meet next year in person. I really appreciated meeting everybody last year in Zurich in summer, having time off, having time out as well, next to all the intense presentations. Now, I do hope that the one benefit we're getting this year is that we have a lot of more attendees. We have more than 1,600 people registered. And without long introduction, I would like to show some of the highlights that we have achieved as a developer community over the last year. So we really planned for this event to have 400 people. Now we have a lot more registered. I am expecting that people will dial individually into particular sessions. So I'm not expecting everybody to be here for the opening keynote. And a quick introduction of myself. Ramon has already introduced me. I have founded a number of open source projects back as student over 10 years ago, 12 years ago, the first one. And these are forming together the PX4 ecosystem. And by now, I'm really the chief cheerleader of that ecosystem, but we have a lot more developers that are pushing this forward, in particular, of course, Daniel Agar, who is taking the technical lead. Now, thanks to the fact that we had to go virtual, this is a truly global event. we're really stoked how many people are dialing in from literally almost every continent. I don't know if we have Antarctica, but other than that, I think we're pretty covered. And so I hope that this will spur further discussions, more contributions from across the world. With that, big thank you to all of our contributors. We have hundreds of contributors across all the different projects. This goes way beyond PX4 firmware. We have things like Mav SDK, we have the simulator, and all of those have lots and lots and growing of contributors. So thank you for doing that. If you haven't contributed yet, there is a session in the program. Please look it up, how to contribute. Please approach us on Slack. If you're not quite sure what contribution means, it typically means taking a change, an improvement, or maybe just a bug fix, and sending a pull request on GitHub onto one of our repositories. So please keep doing that. And I'm pretty sure we didn't capture all the profile pictures of every single contributor, but these hopefully stand in for all of you who have contributed code, have contributed documentation, have contributed flight testing. And so big thank you. This community, this open source project really relies on you, and we would be nowhere without your continued effort. Thank you. So for those of you who haven't been with us for years, maybe this quick recap of our history is an helpful introduction. So I'll usually do this quickly every year. Pixhawk really started as a student team at ETH Zurich in 2008. We wanted to do autonomous flight using computer vision on drones. Back then, you couldn't buy autopilots. So we ended up building our own and then making the hardware and software available as open source and open hardware. And this is really what started this ecosystem, because other people came in, piled in, helped to develop that. Now, 12 years later, we really start to shape up industry standards that are actually adopted beyond the coverage of just core open source as an open source project. But even companies like Skydio or Parrot are implementing, for example, our ground station communication standard in their latest commercial models. With that, feel free to look that up. There's also a history on our website. We've come a long way. And I believe that the adoption of open source software will grow further, because as these machines, as drones, as autonomous systems become more and more complex, you really need a very deep software stack. And PX4 itself is, by now, I would call it more like an ecosystem, like Linux is an ecosystem. It's not just anymore the core PX4 kernel. And so that growth is forcing more and more individuals, and in particular also companies, to adopt open source software, because that's the only way how they can keep moving. Otherwise, they would need hundreds of developers in every single company to achieve that, and that's just financially impossible. So things look great, and I hope that a lot of the companies that might still try to do things themselves or everything themselves will come around over the next 1 or 2 years to adopt PX4, because at the end of the day, that's really the only way to sustain software on drones going forward. Now, the other question that often comes up is like, okay, but how do I really build my product? How can I use the same code as everybody else and then not get kind of just turned into a pure hardware company and have no profit, have no differentiation? Now, the way to do that, you can use open source software, is you have your product and you build that product at a particular point in time, maybe 2017, 18, whatever it is. And typically that involves the industrial design, that involves the whole airframe, that involves the whole system integration. Now, Back then, you didn't need to have obstacle avoidance or computer vision or safe landing planning or anything like that. Today, customers kind of expect that. So the cool thing is, if you build that on top of an open source ecosystem, you can bring your product along. So instead of just having now to re-engineer all of that, you can just put it on top of more technology that becomes available to you over time. So this is how you sustain your product on open source. And I'm expecting that most of you on this call will understand this, but maybe you can pick this up as a way to pitch it to your management why you should and can work more intensely with other developers. Now, let's look at this year, 2020. What is PX4? It is still very much what it was last year, which is an open source project that is used in 3 core industries: consumer, commercial, which includes government usage, and what we call industrial. Industrial is a bit emerging. So consumer, we all know consumer drones. There's, of course, one elephant in the room with one very, very big company that has a lot of market share, but there are still a lot of companies that use PX4. Most of them don't talk about it. In commercial, people are much more proudly talking about PX4 because it is about interoperability, standards. Their customers usually want to know what's inside. They want to know, is that a software I can trust? Is it transparent? And so that's where we have right now a lot of traction, and I will have quite a few examples of that in the rest of the presentation. Now, an upcoming industry, and actually the biggest difference between last year and this year is in that sector, are industrial applications. And to me personally, the main difference between commercial and industrial is commercial is kind of a better consumer drone. It's a bit bigger, it's a bit more reliable. It is built for workflows rather than personal joy. Now, industrial drones are built for continuous heavy operations. They're waterproofed. They are fulfilling certain safety regulations and standards. They also are often a lot bigger. And that includes cargo drones, flying cars, urban air mobility. I think PX4 right now is not something that's built for urban air mobility, but as we clock up more and more flight hours, who knows where we will be running in 3 or 5 or 10 years. And we see that as a big trend across the whole industry. Governments and corporates are going more and more open source. And that's not just Microsoft with GitHub and Visual Studio Code. It really is also Microsoft partnering with the PX4 community and deepening that relationship. We have a great presentation from Microsoft on simulation, on their integration with AirSim. Check it out in the program. And then also GE Aviation has partnered up with Auterion to use PX4 in their safety critical autopilot. Also great presentation on that topic by the GE team. Check it out in the program. Now, there's one interesting thing that I'm lately spending more time on explaining, and that is the difference between PX4 as a technology and PX4 as an ecosystem. And it's a bit the same thing as with the Linux kernel and the Linux ecosystem. The PX4 ecosystem is really with PX4 at the core, which defines the core interfaces, the core technology. And then you have a number of open source projects like Ground Control and Mav SDK around it, which are also technology fundamentally. But now we start to have more and more industry standards. And these industry standards are standards that we are implementing certain software functionalities, certain interfaces, like Pixhawk, like Mavlink. They have been around before, but now we're becoming more clear about the boundaries, about the functions. And there's the industry association. And there we did one clarification recently. Dronecode has always been confused with PX4, like I'm running Dronecode, or what is Dronecode, or is Dronecode a company? No, it's a Dronecode foundation, and that's how we will start to consistently call it going forward. It always has been a nonprofit in support of open source, a collaborative project by the Linux Foundation, but we'll just call it Dronecode Foundation, and it's really clear. So that's the industry association behind the PX4 ecosystem, which is helping to organize this event, which is helping to organize our YouTube channel, social media, which is contributing the salaries of our program manager, Ramon, and of Ginger, who is working with our community. And then, of course, also really important, there are third-party projects, and this isn't meant as like dismissive third party, this is meant as very respectfully. There are integral projects that we really need to function, like ROS. And we'd love to have a really close relationship. We have one of the ROS founders, Tali, presenting here as well. And our goal with them is to just work really closely together and maybe converge on an ecosystem level the same way as, I don't know, Docker and Linux work really well together. So also really important. Now, one of the urban myths about Linux is that it's developed by hackers sitting in the basement of their moms, which is not quite true. Linux is, for the past probably 15, 20 years, developed by professionals working at large corporations, at IBM, at Red Hat, at Intel. And the same is very much true for PX4. Initially, it was driven by researchers, enthusiasts, hobbyists, but that has changed over the years relatively rapidly. So today, over 85% of contributions are coming from enterprises. And those are typically not IBM's, but Microsoft, for example. But it's really companies using the software. And so we're continuously working with them. And one of the things I really want to make really clear as somebody who is both affiliated with PX4 and Autharian, really today it's all about PX4, and we're just showing the individual companies who are contributing, including Autharian, which has a big share here, because we want to make that transparent also in a way to thank you, those companies, for their continued contributions. In terms of countries, also no big surprise there. As Autharian has a lot of R&D in Switzerland, we have a lot of contributions from Switzerland, but we also have contributors, developers in the US, and a lot of other companies who are US-based. So you see quite interesting pattern with Switzerland, US, Australia, Portugal, New Zealand, not quite expected. And we, of course, hope that other nations will pick up here. And so in particular, if you're from around the world, if you're in Asia, make sure to see what you can contribute going forward so those bars change a bit. In terms of firmware contributions, we've, again, split that up between individuals who work as consultants and corporations. Those are the top 6, or rather top 5, plus the accumulated contributions. You can see, again, Autharian is doing a lot as a company. That makes sense, given I started on my open source mission 12 years ago, and the company has become part of that. Q Ground Control, we see that Don is super active. Congratulations if you're watching, or if you're watching a recording of this. This ecosystem really benefits from you, and great work on Q Ground Control. And then again, simulator, avoidance, you can see where individual efforts are really focused. MNAV SDK, which is our SDK, our user space API, and really, really important going forward for the further adoption of PX4, because just working on the core flight controls is way too hard for many developers. Documentation, again, something that we're heavy. So now we know who built PX4 over the past year. Now let's look at who is using PX4. That's hopefully long-term the same, but right now it isn't always. So we have leading products and developer platforms that are being built. I'm not going to read all of them. Just have a look at the logos, have a look at the systems. It is awesome to see that diversity. We have airframes that weigh hundreds of kilograms or hundreds of pounds. We have airframes that are a pound. Really reflects also the technical capability of the software stack supporting all of these applications. I want to show a couple highlights. This is probably the most crazy example that I have. So let me quickly just play the video. And it's a quite surprising use case, something I totally would not have anticipated, that somebody would actually go ahead and fly a VTOL with PX4 as a person. That's pretty crazy and inspiring. Awesome. So I don't want to steal the thunder of the person who did this. So this is an old video on purpose. They're much cooler, much newer videos. So if you're interested in that, check out the talk of Julian tomorrow. Make sure to dial in. There's the time in Pacific Daylight Time. You can also find it in a program. Really, really mind-boggling, very experimental. Now, a little less scary, but still big, is this cargo drone by Valanzi, also running PX4. This is a public safety firefighter drone by Impossible Aerospace, also running PX4. This here is a cargo drone that is also PX4 based, has made the news recently. This is a government drone, also by Vantage Robotics, also brand new, pushing into the market, running PX4. This is another cargo effort for medical cargo by Avi. Really awesome to see the diversity, as you can see here. Most of you will have seen the unique products that run PX4. Then we have a waterproofed VTOL by Quantum Systems. You can even see the custom pitot tube, heated and everything. So really cool to see that industrialization that PX4 is on right now. We have the FreeFly Alta, and this is the Alta X. Really, really big drone, being able to lift really heavy camera gear, used in Hollywood. Really cool to see what they're doing and the flight performance they're getting out of it. And then this is Elroy Air with this in the background is not a toy aircraft. It's a real Cessna with a huge cargo drone based on PX4. Really cool. And then this is a recent startup from ETH Zurich, also running PX4 on their overactuated. Usually multicopters are underactuated. This one is overactuated inspection drone. Really cool. And then, of course, a company you will have seen before, one that is very close to where I am right now, Wingtrum, with a super cool tailsitter that is based on PX4 as well. So huge variety in weight, in size, in actuation, but all running the same flight control core. With that, let's look at what will carry this open source project into more applications going forward, and those are new partnerships. So Microsoft is not a new partner from last year, but they have renewed their push for integration. We're working with them on AirSim. Super cool. Check out their newest blog post on it. We've recently announced a partnership with ARM/Linaro/96 boards which is their hardware standard for ARM boards. We're going to do a common standard together that's bringing the compute board standard and our FMU standard, and is going to put that together into a smart autopilot, similar to, for example, the products from Modal or from Auterion Skynode that you've seen recently. So let's quickly talk about a couple more developer-focused topics. Developer workflows. So we're doubling down on testing, and we have two awesome talks. Others will touch that topic as well, around improving testing, including having fault injection in more places in the system. So super important for the further hardening of PX4. And we're also going to have a restarted and increased flight testing powered by the Dronecode Foundation for PX4. Board support and hardware testing. We have clarified how we do board support in this project. So there are new 3 categories: officially supported boards. Those come with the Pixhawk standard, manufacturer supported, and experimental. You can read that up, it's online. And we're adding more and more of these hardware targets to the test rig. This is work that Daniel is doing, maintaining, pushing. Big thanks to you, Daniel. This is really important to spot regressions early as we move very fast with the code base. Good. User space APIs, ROS2 support. There are 2 cool talks. Please check them out. We are integrating more and more deeply with ROS. They're coming the embedded way. We come with our publish subscribe framework their way. Really great collaboration for the last couple of years already. And I think it's now ready for prime time, also with us having finally Ethernet on the flight controller. Mav SDK, you already have heard about it. It's the SDK for our ecosystem. Check it out on mavsdk.io if you're not familiar with it yet. Not going to spend too much time on it. It's a simple way to interface to PX4, and that should do it in terms of description. In terms of safety and certification, lots of talks from Chris Anderson, from James Howard, and from Gokul Krishna Srivasan on various aspects of safety and certification. BVLOS, which is one of the key drivers behind wanting to do certification. So please check out those. With FMU v5x, we've really laid the foundations on hardware standards for that. And now a number of companies, GE Aviation, NXP, Auterion, are all pushing towards that within the open source project. And we're going to try to bring ISO 26262 road vehicle certified parts and technologies and approaches into the drone space, which is a lot more lightweight than aviation certification, but still has very, very high pedigree and is accepted as being really reliable. I will quickly dash through the Pixhawk standards so we have enough time for the Q&A. So Pixhawk standards, what is that? Like, you know the Pixhawk autopilot, which is the initial hardware that I did with collaborators back in the day, 2013, and which is named after the student team at ETH, which started in 2008. Now, it's becoming a new life again, this time as standard, because really what Pixhawk created with being open hardware is creating a hardware standard, because people took that design, engineered around it, and so we essentially created a whole hardware set that is why a lot of drone software stacks, drone hardware actually work together, because there was this pseudo standard. Now that the drone industry is getting more regulated, more professional, we're actually turning this into a true standard body like Bluetooth or USB. So think of Pixhawk going forward essentially as the Bluetooth for drones. Poor comparison, but it kind of works. So the goal is to specify all the key components and interfaces correctly so that anyone can build to that spec. And we can enable people to have flight controllers that can be mounted properly into drones with zero compatibility issues. We can enable folks to have really easy to use gimbals that can be just snapped on. And the hope is to really create the same plug and play experience that Bluetooth or USB offer to end users. So it's not just about technical, safety norms and anything. The goal is interoperability with that. And the driving factor from a software perspective are Mavlink, are PX4, but really the standard is standalone. So if you had a different software stack or proprietary implementation, you can still do that. And that allows you, for example, to create a custom payload that is completely your product to interface to that standard. And so it will work with all those PX4 driven vehicles. Check it out on pixhawk.org. I will do a quick high-level overview now, though. So one of the core pieces is the autopilot bus. We've seen that many different companies had many different autopilots. For me, an autopilot, having designed quite a few, is actually not too complicated. It's a microcontroller connected to 3 sensors, a bit of power management, and that's about it. And the problems we have seen supporting these different boards and regressions and power supply issues and whatnot were horrendous compared to the inherent hardware complexity. So the pattern over the last 3 to 5 years, ever since we had more and more variants based on this old Pixhawk design and people didn't just re-implement the very core design, we spent a lot of time on this. So the solution to that is to standardize this much more closely so that we can guarantee that if you implement to the standard and you run PX4 on it, it'll work. It'll work every time. You will not have weird power management, power on, power sequencing issues like we have seen them in the past. That's what this is about. So Pixhawk Autopilot Bus is specifying a footprint for autopilots. And the matching standard for payloads for gimbals is the payload interface standard, Pixhawk Payload Bus. And that is essentially the mechanical connector, how you connect, it's a dovetail design, how you connect the gimbal to the body of the drone. It is the software, which is specified as Mavlink, camera and gimbal payload protocol. Electricals, we are supporting USB and Ethernet. And with that together, you can really build a completely standalone gimbal that is not related to any particular drone that will work on a number of vendor systems. And the first company going to market with that standard is FreeFly, based on what I'm seeing. And I'm really excited about that because this industry needs that. There's way too much fragmentation, and all this system integration engineering work is cost for a lot of people in this audience that doesn't add any value, doesn't really further your business, and is also sometimes a reason to not use open source, because as long as you have vendors that are vertically integrated, like DJI, and it's just easy and it just works, and you have a lineup of payloads, you're going to go with that vendor, even if the drone isn't exactly what you need, because you just have better choice taking the picture, which is what really most people care about. And so as you approach this, think again about it if you really needed your vertically integrated special solution, or if you could just go with something that is a bit more standardized, gives your customers more choice, and maybe that's driving, in the end, a lot more business than going after the last bit of specialization. Now, for the specific autopilot, to ensure that we can really run the software successfully, we also need to specify how exactly that autopilot is built internally, not just a connector. That's what these FMU, for Flight Management Unit, V5X, V6X documents and standards stand for. The X at the end is actually indicating the industrial version, so that's the hardened design without X. it's the more developer enthusiast community version. We're targeting roughly 1 version per year. We're on track with that with V5X and V6X. And the cool thing is those 2 designs are interchangeable on the Pixhawk Autopilot bus. Good. Another important problem, interfacing motors, interfacing ESCs, interfacing servos, and other actuators. So that is something that we're attacking with a new CAN-based interface standard. Think of it as Wi-Fi for drones, of course, not wireless, but it's a high-level spec that includes messaging, includes authentication, includes deployment and software upgrades. So it's a lot more than just a transport layer, and that's why it will sit on top of UAV CAN v1. It's not on the same thing, it's not competing, it's standardizing a message set and state machine on top of a UAV CAN v1 transport. And check out the call from, the talk from Peter, and of course from Pavel, who is also giving us an update on UAV CAN. Good. If you're interested in standards, there's a panel on that next week. Tomorrow. So check that out. If you want to ask more questions, follow the discussion there. Looking forward to that. Then we're almost at the end of the presentation. There's also an update on how we do releases and roadmap. So in terms of releases, Daniel and I talked about being kind of really stuck in this release stabilization process for weeks because people come in with feedback, but it takes quite a bit of time to test. And then because the releases are really major steps, major performance wins, but also API changes and kind of hard to digest. We want to make it simpler and easier to stay closer to the current version in upstream. So there will be more frequent releases with gradual, gentle changes. That makes releases more predictable and easier to scope because we're not having this sort of big step. And that should shorten the cycle between downstream adoption and feedback from companies using it. That will also mean, however, that you will have these small increments all the time. And so if you need something super stable, you need to have your own strategy to stabilize that, also API stabilize that if you want to stay on an old release, which might have been easier with the only 2 releases per year up until now. We believe this will tremendously accelerate our development. It will allow us to bring improvements in faster. And we think that's the right thing for the upstream project. For individual products, we believe that that's a responsibility of each company to create those stable releases for them if they want to freeze things, on a longer time frame than that. Good. Then one last slide. One thing we really don't want to do is to commit too specifically on goals. This is a meritocracy, so it's contributions done by individuals, done by companies, based on best effort, based on when and if they have bandwidth available. But this is roughly what we know our developer community is going to work through the remainder of the year. We're changing the way that the EKF framework is derived to Python to make it more approachable. That's something that Roman initiated, and Paul is now on that as well. So that's really cool. That hopefully opens up more contributions into our state estimation framework. We're working on multi-EKF support that is related to some of the industrial applications and industrial drones. Much more component level testing. Again, check out the talk from Julian about fault injection. We have a new way to allocate control signals to multicopters and VTOLs, which will allow us to develop the flight control architecture in a much more scalable fashion. And then CAN is the other main part, plus quite a bit of hardening, cleanup, structure, like in the Commander and Navigator, hardware-in-the-loop testing, all those things. There are probably a dozen things I haven't mentioned here. There's a lot of work on computer vision, a lot of work on autonomy, but that is sort of in the wider ecosystem, and these contributions will come in as they're ready. Cool. So that was really what I wanted to get across. Now I'm looking forward to check out your questions in real time. They're appearing on a screen in front of me. First question, how do you see the PX4 platform in the upcoming years? So I think I mostly talked to that, but just let me recap. We expect it to continue to have all the properties for consumer drones, also for recreational use. We plan to invest into auto-tuning, so it's more approachable, in particular also to software developers who might not know how to tune a drone. So the goal is to keep that foundation solid, make it even more approachable, but then a lot of effort is going into commercial and industrial applications. So it's about all the upcoming reliability requirements, all the upcoming regulations, and there we will invest a lot of energy to make sure that PX4 continues to be the best base for a commercial drone product. Second question, is PX4 all about the software side? I would say the PX4 ecosystem is not, as I've shown you with Pixhawk hardware standards. PX4 as sort of a project, yes, it's very focused on software, and that makes sense. But you can see that in the whole ecosystem that we're supporting with Dronecode, it's very holistic, it's full stack. How can interested students get involved with the PX4 community? I think the best way is to join Slack. Our Slack channel, it's slack.px4.io. You can get yourself an invite there. And our forum, which is discuss.px4.io. Question, new company in the drone industry, how can we get started? Well, that's a difficult question because it's so open-ended. It could mean anything. Do you need to find customers? Do you wonder how you can work with PX4? Probably just send me a private Slack message and we can figure it out. Does PX4 have any plan to expand its market to other nations? That's an interesting question. So what I'm taking away from that is that you kind of think or assume PX4 is like a vendor. It's not. It's an open source project. It's in the internet, so it's in any nation available. And we're not expanding, we're not pushing, we're getting pulled in different adoptions because people just download the source code, get successful with it, contribute back to it. So the answer is we get in many different nations all the time. Because people are successfully using it. What about certification? Are we working with FAA? Yes, we're working with pretty much any regulatory and standardization body under the sun. We're working with the FAA on type certification. Check out Chris Anderson's presentation in the program. We're working with EASA. We're working with ASD Stand. We're working with ASTM. Very deeply involved, and typically that works through individual companies that are core PX4 contributors who are present in these standardization bodies. Is it accepted that automotive standards are accepted by EU regulators? Yes, absolutely. We also expect the FAA to be totally happy with that. In fact, you can prove that the automotive safety and integrity levels can be mapped to DO 178 levels. You can Google for ASIL DO 178 mapping, and you can find documents that people actually have done it before. So we're not just speculating. This is based on other people successfully doing it. Good. Thank you for watching. And please enjoy the rest of the summit. And then I'm looking forward to more great talks and meeting you in person, hopefully already next year.
Hey, looks like I had no audio before. Oops, live. I guess, thank you. Thank you, Lawrence. That was a really interesting session. Very informative, packed with all the info, everything we've done throughout the year. Feel free to drop in Slack or questions on chat. We're looking at them and we're putting them in front of the speakers for you. Right now, we got the next speaker coming up. Give me a few minutes. I'll load it up for you. Hey everyone, I'm back. So next up we got towards a lightweight software architecture for PX4 computer vision. It's a session by James Strawson. James is a senior roboticist at Model AI, and he's calling in from San Diego today. Um, James received his PhD in robotics from UCSD, where he also taught classes on 3D printing, mechanical design, feedback control, and embedded systems. Wow. Before joining Model AI, James created the Robotic Cape and EduMeep development platforms, as well as the Lib Controlled Robot open source software package for the BeagleBoard.org Foundation. At Model AI, James enjoys designing lightweight control and navigation algorithms for robots that run on embedded platforms. All right, guys, let's hear it up for James.
Hello, hello, testing 1, 2, 3. Okay. Okay, you can hear me now. Okay, technical difficulties, that's to be expected. Okay, so some of the fundamental computer vision tasks that you're going to want to start experimenting with and plugging into the PX4 ecosystem is going to be crucially visual inertial odometry, so that you can do very precise position feedback control, as well as navigation in indoor environments. The fiducial marker relocalization is the next step that's going to try and compensate for some of the shortcomings of a visual inertial odometry system, which is knowing where you are relative to the world around you, as opposed to just where you are when the odometry system started up. And then finally, you may want to use one of PX4's newest and nicest features, which is collision prevention. This is something that can easily be done with a stereo camera pair, along with a host of other sensors. But for this presentation, we want to focus on computer vision. And so I'm going to talk about how to use stereo cameras for this. Now, a big part of connecting higher level data, such as odometry, into PX4 is just plumbing. It's getting data from the right sensors to the right algorithms, and then finally into PX4 itself. Now, there's a lot of examples online that you can find around based on ROS and Mavlink router. These are great methods to get you started because there are examples available. However, if you're comfortable with it, just reading and writing UDP and UART packets, that's something you can easily do yourself if you're comfortable with it. The more complicated step is keeping track of all of the frames of reference that the data comes in and the frame of reference that PX4 expects the data to be in. So ROS and TF2 are very good tools for keeping track of different frames of reference and moving data around between them. Or if you're comfortable, I can show you how to do some of that math by hand so that you can more easily optimize it or fine tune for your platform. And then finally, my colleague's going to talk about some of our experiences with an open source VIO algorithm, Vince Fusion. So the fundamental basis for a lot of what I'm going to talk about all depends on visual inertial odometry. So here you can see a drone flying with no magnetometer and no GPS. This is purely based on visual inertial odometry. And as you can see, this allows for extremely good position control, as well as disturbance rejection. As I push the drone around, it's very stable and very easy to fly, especially in very tight indoor environments with a lot of backwash off of walls and furniture. So to get this to work, you're going to be taking data out of your VIO algorithm of choice. There's dozens and dozens of ROS options online that you can start playing with. But whatever you choose, that data has to be passed through to the PX4 autopilot in the form of a Mavlink packet. And whether you use TF2 or other ROS tools or Mavlink router, you still have to make sure every step of the way that the data is correctly rotated and translated into the frame that PX4 expects. You have to choose the appropriate Mavlink packet for what you're trying to do, and you have to make sure that the data is timestamped correctly. If you're using MavROS, then MavROS is going to handle a lot of the time syncing for you. Otherwise, you're going to have to make sure to do the time syncing between your onboard computer and the PX4 autopilot yourself. Now, your first option for Mavlink packets that you can send into PX4 is the vision position estimate. This is the first one that you'll see in the PX4 odometry documentation page. And it's extremely simple. You're just sending in the drone's position relative to the local frame in X, Y, and Z in meters. This is going to be like the NED coordinate frame, northeast and down, or since this isn't necessarily lined up with north, it's more appropriate to call the local frame aligned with forward, right, and down as the odometry system is when it boots up. You can also send in the roll pitch and your angles of the drone. Now, if you want to be a little bit more fancy, you can give the EKF2 Kalman filter inside PX4 more information to work with, and therefore give you much better precision control and accuracy by also sending in the first derivatives of the first packets, the velocities in X, Y, and Z, as well as the roll speed, pitch speed, and yaw speeds. Now, something very critical to know when you're sending this data in is that the frame of reference for the first derivatives are going to be in body frame, not in local frame. So while we say that the X, Y, and Z position of the drone is the position of the body in local frame relative to where it started up, the velocity is actually going to be the velocity of the body of the drone relative to where the drone is pointing. So a positive velocity in X is always going to be forward along the direction of the drone's nose, so wherever the drone is pointing, not the velocity along the local X-axis. You can be very explicit with the frame IDs. So here I've used the example of the child frame ID being body frame and the primary frame ID being local frame. This is most likely what you're going to use. Now, once that data is going into PX4, I think you'll find the experience is very good as long as you understand this plot and understand exactly what it means to be sending data in body frame and local frame. So each of the green boxes here is a frame of reference. It's defining a coordinate system. So for example, the body, this coordinate system is aligned with forward out the nose of the drone, right, and then down. This is also centered around the center of mass. There is an option in the EKF2 parameters of PX4 to define the center of your visual odometry data as offset from the center of mass. However, if you understand all of these frames of reference and you're going to be doing rotations and translations in your VIO algorithm anyway, I think it's definitely worth going the extra step and making sure that the data is going in correctly in the first place. Then you don't have to worry about tweaking PX4 parameters. Now, each of the blue boxes is going to be a transform. So that's going to consist of a rotation and a translation. Translation is a simple 1x3 vector, x, y, z, whereas the rotation can be represented as either a quaternion, a roll pitch yaw, or a rotation matrix. For simplicity of the math, I highly recommend just using rotation matrices. However, TF2, if you elect to go that route, will handle all of that in the background for you. So the data that you're really going to get out of a VIO algorithm is not this body with respect to local transform. It's actually going to be IMU with respect to the VIO frame. So the vast majority of VIO algorithms are going to represent the position of the IMU relative to wherever the IMU was when it booted up. Now, the IMU you use for visual inertial odometry is not necessarily going to be aligned up with the aeronautic coordinate frame forward, right, and down, nor is it necessarily going to be aligned with gravity. And so I highly recommend doing the next step of having another rotation to go from VIO's frame of reference to a gravity-aligned equivalent. So this rotation between VIO and VIO gravity-aligned will have no translation. It will simply have a rotation to correct for the angle of the gravity vector inside of VIO's frame. You will then also have to rotate to local frame, which is most likely going to be the opposite of IMU with respect to body. So you'll have to undo this twice. You'll have to go from IMU to body and then VIO to local. And then this is an optional step to go between VIO and VIO gravity aligned. Now, once all of those are in place, you can start doing something a bit more advanced. So here we have the drone has started with the VIO frame purposefully offset and crooked from its landing pad. And I have a small Mavros-based node running, which has just told the drone to go forward and back a couple of meters along the line of whatever its x-axis thinks it is, which in this case is off crooked. Now, as it reapproaches the landing pad, the camera suddenly sees the landing target and has now made a correction to that offset. So the drone was flying in local frame before, which was offset due to the crooked VIO frame. But then as soon as it saw the landing pad, it's made a correction from local frame to what I like to call fixed frame. So local frame is going to be aligned with wherever your IMU was when VIO initialized, and it's going to be your job to calculate the translation and rotation between the local frame and fixed frame, which is defined by fiducial markers or some similar localization system. You could even use a GPS or a magnetometer to do this, but April tags are a very available open source method for doing this. Now, much like we had a chain of transforms and rotations to calculate out the body with respect to local frame, this is just a case of calculating this by multiplying the rotation matrix and transforming each of these steps. So you do multiply, add, multiply, add, multiply, add, multiply, add, and then finally you get back to this link. Now, the final sort of fundamental computer vision technique that you're going to want to play with is PX4's collision prevention feature. Now here we're using a stereo camera pair looking forward at the wall, and as you can see, it doesn't matter how hard I push the stick forward, the drone is not going to crash into the wall. So I can freely move back, but as I try to go forward into the wall again, it's going to prevent me. Now this is the collision prevention itself, and the processing of my radio control input is completely being done in PX4 right now. All I'm doing on the onboard computer side is transforms and rotations of the stereo data into the format that PX4 expects. So this is the data structure that you're going to want to keep in or send into PX4. And the data structure is very much going to look like a spinning LiDAR sensor. So it's called the obstacle distance, and it's Mavlink message ID 330. And it's a very flexible Mavlink packet. It lets you send in up to 72 different distances spanning around the drone. Now, you don't have to populate all of them. For example, here, the stereo camera pair that I showed in the last video has a field of view of 65 degrees. And so if we split the 360-degree field of view up into the 5-degree increments, then we're only going to use the center 13 of those. It's helpful to know that these distances and the array that contains them starts pointing forward and then spins all the way around to the right. So here we have distance index 0 is pointing straight forward, and then it's 5-degree increments all the way around. If you want higher resolution, you can decrease the increment value to something less than 5 degrees, and then you can have, let's say, higher resolution in this forward-facing area, or you can just leave it as 5-degree increments, and then you'll see all the way around. Now, to get there, you're going to have to take the point cloud that you get out of your stereo camera and do more transforms and rotations. Primarily, you're going to have to take the stereo camera field of view, which is Z out of the lens, X to the right, and Y down, generally. Rotate that into body frame, and then ideally put that also into a leveled out version of the body frame. So in the same way that we had a rotation between the VIO frame and the gravity aligned VIO frame, we're going to do the same here, going from body frame to a leveled out version of the body frame. Now, a very easy way to do this, a very computationally efficient way to do this, is to take a vector which is pointing down along gravity, so +1 in the Z direction, straight down, rotate it by our rotation matrix defining body to local, which is what we already set into PX4. If we take the cross product of those two, then what we're going to get out is 1/3 vector, the cross product, which is going to define the axis that the body has to rotate about to go from where it is now to being level. And then the 2 norm of that vector can be arc signed to get the angle. Now we have a rotation in axis angle format, which can very easily be rotated or transformed into a rotation matrix, a quaternion, roll picture, however you like to represent your rotations. This is a very computationally efficient way to do this, and it also works well for the VIO gravity aligned frame. Now I'd like to see just what you get once all of these are in place. So this is an open source MavROS based node that we have available on our website that sends in a smooth trajectory into PX4 that defines a Bernoulli's lemniscate, also known as a figure-8 pattern. And so this is sending into PX4 a position, velocity, and acceleration at 30 frames per second. And what you get is a perfectly smooth trajectory. Now I'd like to hand it off to my colleague, Hitendra Gangani, who's going to talk a little bit about the open source Vince Fusion project and our experiences getting it to work with PX4.
Thank you, James. And hello, everyone. So in the interest of time, I'll just jump right into it. So I will be talking about our effort into working on a open source BI algorithm called as Vince Fusion. And so we wanted to share our experience about the approach that we took, the changes that we had to make to get real-time performance, and the kind of problems that we ran into. So to begin with, what we did was we tried Vince Fusion on a regular desktop PC, but using our own ROS bags. So our ROS bags were collected on the system on which we eventually wanted to run Vince Fusion live with PX4. And the ROS bags that we collected were both handheld as well as in flight. So the reason we took this approach was because it helps resolve a lot of fundamental issues like the extrinsic calibration, wherein you have to give the IME to camera relationship, the intrinsic camera calibration, feature tracking as to how many features you want are good enough, or what should the distance be between features, and anything that will help you get good feature tracking. Another important thing that we can tweak during this process is the IMU noise parameters, which is the axle and the gyro noise deviation and the bias. And while we are working on these issues, we also realized that there were certain assumptions that were made, like the focal length being of a particular value and the way in which the IMU only post generation was being done. So even though we were working on a PC with our ROS bags, we were able to iron out all the issues in order to get it working stably on a PC with our ROS bags. So once we had this consistently working, then we made the switch to moving from the PC to the actual drone on which we wanted to fly WinFusion with PX4. And then once we moved there, first step was to make sure that the ROS bags that work consistently on the PC works really well on the onboard computer as well. And then we moved from using the ROS bags to using live camera and IMU data. And since the PC is going to be much more powerful than your onboard computer, we had to deal with the real-time performance. And what we noticed was that if we are not performant enough, then the functionality also starts breaking down. So we had to resolve a lot of performance issues so that the functionality stayed intact. And some of the things that we did was to use GPU for feature tracking instead of the CPU, some optimizations related to Cirrus Solver, specifically in WinFusion. And then instead of consuming, let's say, features in every camera frame, we said, let's try and consume features from every other camera frame. And another thing was related to that we have just recently discovered is issues related to threading mechanisms. So we need to have very efficient threading mechanisms to gain real-time performance. So these were some of the performance issues that we resolved to get a good functionality as well. And the final step was to try WinFusion with PX4. And the first step was to send the WinFusion data to PX4. And the way in which we did that was using what James mentioned earlier, using the Voxel Vision PX4 that we have. So we sent the WinFusion data using that mechanism. And there were a few, the problems that we ran into when we did that was sending incorrect parameter for the VIO data, specifically, like James mentioned earlier, it was PX4 expecting the VIO data to be in a certain frame of reference, but we're not sending it in that frame of reference. So that's what I mean that here. And then as far as pose is concerned, it's sending the timestamp mechanisms wherein if you lag the pose by a lot as compared to the current time, then the VIO packets were getting dropped. So this is just a quick video of where we stand. This is using WinFusion in hold mode is what we are doing here. And one of the things that we are experimenting with right now is to update the pose using IMU data only, using a good camera pose as a baseline, but something that we are just been trying out recently. Thank you very much.
Thank you. So let's see what questions we have come up already. Good, we have lots of questions. Let me swap back to my video so you can see me. There we go. All right, so questions. What hardware do you use to run your VIO setup, i.e. computer, cameras, IMUs? So we develop and distribute a fully open source development platform called Voxel, which is based on a Snapdragon processor. And so that's what we use for all of our development. We have wide angle fisheye lenses, which plug straight into the camera ISP of the Qualcomm Snapdragon chips. And so we can get very high performance VIO out of this setup. Can VIO work outdoors with GPS fusion as well? Yes, VIO can work outdoors. You may want to configure it a little bit differently, just basic parameters of the VIO algorithm. GPS fusion with VIO is actually fairly recent development in PX4 itself, and I think we're going to see a lot of tweaking and performance improvements of that in the coming months, in the coming releases of PX4. Derivative doesn't work for discontinuity and corners. How to deal with that? So I assume you're talking about sending in the derivative of the velocity derivative of position that you're sending into PX4 for the odometry. Now, PX4 expects a continuous input, so you should have no discontinuities into the input going into PX4. If you need to handle any jumps, such as when you see an April tag, you need to make sure that the data PX4 is getting is completely smooth, and any adjustments you do to those offsets are taken care of before you send the set point into PX4. So PX4 always needs to be flying relative to local frame. If you have position set points in a fixed frame, you need to translate those set points into local frame first to avoid those discontinuities, since PX4 won't handle them. And of course, we can't have the first derivative of a jump. Have recent ROS versions dealt adequately with their software timestamping issues? Previous versions did not provide hard real-time guarantees on timestamps, causing serious issues with sensor drift in vision processing. If you're going to be consuming camera and IMU data through ROS, I think you'll definitely want to be very sure that the ROS nodes that you're using to publish the camera and IMU data handles the timestamps properly. So that's the wonderful thing about the open source community, is we release the ROS nodes that we all create, and it is the ROS nodes themselves which generate those timestamps. So it's really up to whoever's programming the node to do the timestamp correctly. That's not up to ROS. ROS just sends around the timestamp that it's given in the packet. So whatever driver you have reading that IMU is going to have to do the timestamping. Okay, question, XYZ position with respect to home position. Home position should be fixed then. Yeah, this relates similarly to a previous question where home position is wherever the VIO started up. And so anything that you want to move, anywhere you want to go relative to that, you're going to have to do a transform and a rotation to the set point. So that you can't move that around. Last question, how to use VIO with GPS so the drone can enter indoors doing an auto mission. Isn't that the feature that everybody wants? So I think starting with PX4 1.11, VIO and GPS play a little bit more nicely together, but that's not something that I've done lots of flight testing with myself, but I think we're going to see a lot of development in PX4 with regard to this. So I think that's all of my time, and that was the last question. So thank you all for dialing in. I hope you found this informative. Thank you.
Yep. Thank you. Cutting you out. Bye. Hey, can you guys hear me now? Yeah, guys, sorry. I mean, you know, we've been planning for this event for a couple of weeks now, but live sessions always go the way they're gonna go, right? James, thank you a lot for your time and contributions to open source. It was a really cool presentation, and I'll talk to you soon. Community, wow, welcome. I see like everyone here. Let's see, I get people from Portugal, from Mexico, yeah, USA, UK, Slovenia, Finland, Brazil, Turkey, Colombia, India, Korea, Romania, Myanmar, Indonesia, Canada, Switzerland. Wow, thank you guys. This is awesome. Thank you for joining today. We have a full day of sessions today, so I'm sure you're going to be busy. Next up, we have open source workflow for advanced vehicle dynamics. It's by Matt McCanty and Jesse Hoskins by GE Aviation. While I load the speakers, please stand by. Don't forget to look for the pre-recorded sessions. They're on YouTube channel. Please go and search for those. There's some that are premiering right now as I speak. Pay attention to that, and please follow us on social media. Don't forget to post using the hashtag PX4 Dev Summit. All right, so be right back, guys. Hey, how's it going? So we're back. Next up, we got open source workflow for advanced vehicle dynamic simulation by Matt Bacanti, Jesse Hoskins from GE Aviation. They're calling in from Grand Rapids, Michigan. Matt is the senior product manager for GE, and Jesse Hoskins is the senior systems engineer working with the PX4 flight controls, hardware, software in the loop simulation, and open source accessible aerodynamics modeling of various UAS. This presentation will focus on an open source workflow, implementation options, applications, and demonstration of a civil solution for a 50-pound VTOL airframe and opportunities for future development. And I'm switching to you, Matt. Can you quickly switch to your webcam, please?
Great. Yes. Can you hear me?
I can't hear you. I don't see you, though. It's probably on Zoom.
I am showing the, let's see here. I'm showing that my video is live.
There you go. You're live.
All right.
Got you. All right. It's all yours, Matt. Take it away.
Right.
Thank you.
Thank you. So, good morning, good afternoon, good evening. My name is Matt Bacanti. I'm joined here today with Jesse Hoskins, and as Ramon had mentioned, we're going to be talking about an open source workflow for advanced vehicle dynamic simulation. So the first thing I wanted to touch on is that this is a very broad subject area, a tremendous amount of information that can be discussed in the overall dynamic and the different tool chain that can be used to address this. In fact, the OpenVSP, which Jesse will be talking about a little bit later, has an entire conference track and information associated with it. So our objective today is to work through a high-level overview of this information to arm you with information of how you could best use this in your development workflow and process. And while we mentioned an entire different components of the workflow, you see those identified here up on the slide, the two specific areas we found most valuable and interesting are OpenVSP and JSPSim. And given the amount of time that we have today, that's what we're going to be focusing on. So what we're going to be covering today is the why. Why would you use this particular configuration? At a high level, how? And then some demos, the what you can support and do. Again, we want to make sure that people come away from this presentation with an understanding of this at a high level, and to be able to identify critical flight control characteristics of their vehicles and simulations. Another note is that the information we're sharing here today is not the be-all, end-all solution. There's multiple different ways that we'll talk about that you can support, but this we found to be meeting kind of that golden 80-20 rule, where we're identifying those 20% of inputs that are driving 80% of the outputs, and specifically how that relates to the broader performance of the vehicle itself. Now, jumping into a high-level implementation here, and that is how the back-end civil solution is actually functioning. So first and foremost, the work that has been conducted here has been heavily supported and influenced by a number of different individuals, including team members that we have in Mexico, Poland, and in the US, as well as adopting a lot of the great work that the open source community has published. Specifically, we'd like to recognize Roman and the work that they did originally on some of the Hill work, which we've taken and adopted and used for this particular scenario. If you look down on the bottom, when we look at the two key components that we wanted to focus on, one is this airframe definition with OpenVSP, and two being JSPSim. The interaction between these two is the specific area of workflow we'll be focusing on. But another key input that we wanted to identify was the fact that this implementation is slightly different than using flight gear in a standalone fashion. And we'll talk about specifics of how that affects it. But ultimately, the key is that we can run JSP Sim at a much higher rate than you can run Flight Gear at. If you're familiar with any of the general PX4 software in the loop or hardware in the loop concepts, this is leveraging all of those same configurations and components. So why? Why did we go down this path? We started this process about 9 months ago when we were integrating a new airframe with PX4 and new avionics and payload packages. Inherently, that was adjusted the mass distribution of the airframe. We wanted to ensure the changes that we made on this large airframe weren't going to have adverse effects on the overarching performance. And obviously, if you're going to be flying a 45-pound airframe, this is not inexpensive, and it carries a significant risk from an overarching operational perspective. So we want to identify any of those really exciting components of the airframe characteristics prior to actually going and flying the vehicle. And so in that process, the first step that we took was to conduct basically the paper napkin exercise of doing an assessment of the vehicle. And we determined that this particular vehicle with the initial configuration that we had identified had a static margin that was smaller than we would have expected. And for those of you who may not be familiar with static margin, ultimately it is the ultimately derives the fact of how the vehicle performs when it is up against some of the flight envelope characteristics, which would be interesting and important to identify when we're doing a back transition, since this is a VTOL or forward transition. And so we took the opportunity to model the airframe, effectively creating a digital twin that allows us to go take that vehicle, evaluate it, train it, give our flight crew members the opportunity to actually see and feel the vehicle in the simulated environment, plus identify the way that we could either improve that static margin or overarching increase the performance of the vehicle prior to actually conducting that first flight. So now I'm going to hand it off to Jesse, who is going to take us through the next steps, specifically related to the why and how and the what. And I look forward to chatting with you more at the end here in the Q&A. Jesse.
All right, thank you, Matt. So today I'm going to start out by talking about the why with selecting the tools that we did. So we broke the tool chain down into two primary tools. First, an aerodynamic analysis tool. So the table at the top left here, you see that OpenVSP and VSP Aero. That's what we ended up picking. But basically, it's an open source NASA tool that has a linear vortex lattice method solver. Also has a panel method solver to perform aerodynamic analysis. So this level of analysis we found to be sufficient. It's also an open source tool, has a very easy to use GUI. Again, like we had said before, it has a workshop specifically dedicated to it, so it's pretty well supported. We also looked at DigDat, which is the program now that is the digitization of the Air Force's DATCOM framework. So it's a very sophisticated framework, has a lot of history behind it. It's mostly open. There's some GUI components and plotting components that are closed, but one of the things that we noticed was we were looking to model an A-tail, and so some of the complex geometries drove us closer to OpenVSP in this case. We also looked at AVL, which is more of an industry standard tool for this type of analysis, which is sophisticated, it is open. However, we found the learning curve to be non-trivial. So in this case, kind of similar with MATLAB and Simulink in that with the aerospace toolbox, it's very powerful. It's often used in concert with a DATCOM type tool, but it isn't open. It's also probably a little more of a learning curve than we were looking for here. So next we went to flight dynamics simulators. So looking for a 6 degree of freedom simulator that was of sufficient complexity. So JSP Sim is what we ended up settling on. One of the key things about JSP Sim is we were able to run it at 250 hertz and beyond on relatively limited hardware resources. It's also very open and extensible. It can be complex to configure initially at times, but it's very extensible. That was key for us here. We also evaluated X-Plane. The hardware resources required to run at 250 hertz, which is obviously what we'd like to be the EKF and PX4 at, were a little more substantial. And so that combined with it not being open lent us towards JSP Sim. We ended up using flight gear here for the visual front end, but not the dynamics. Basically, it's more constrained than JSP Sim. And we also looked at Real Flight, which is a very good tool. We can run that up at 250 hertz, but it's not open, and that was something that we really wanted to have here. Obviously, Gazebo was another tool, basically the first simulator that we evaluated, and it could function in this capacity. There were some elements of JSP Sim and how the dynamics were implemented already that moved us that way, but Gazebo would also be a completely fit into this framework. So now I'm going to switch to the how. So specifically with OpenVSP, we wanted to take a model of the vehicle, so the geometric and mass properties, and create or perform an analysis to generate the aerodynamic coefficients, stability derivatives, things like that. So on the right side of this slide, we have the mass properties specifically is where we'd start. So there's a lot of ways to model mass properties in OpenVSP. We chose to use point masses, using the inertia calc tool in OpenVSP, able to generate the center of gravity and moments of inertia around the 3 axes. We then took the geometric properties and built a geometric model in OpenVSP. Now, one of the key insights in OpenVSP is how the solvers are set up, specifically within VSP Aero, which is kind of the I'd say more the back end of the aerodynamic analysis. The simpler geometrically, the better it will perform. Specifically with the vortex lattice method that we were using, since everything is modeled as a lifting body, mainly the dominant aerodynamic components should be modeled. So that's your wings, your control surfaces, your stabilizers. Everything else contributes to drag. We did have another method of building up drag that OpenVSP, the workshop actually recommends. So we found it to be sufficient to model the wings, control surfaces, and stabilizers. So with that geometric model, we were able to iteratively run VSP Aero. So you can do computational sweeps over varying flow conditions. So your angle of attack, your side slip angle, Mach number, control surface deflections, etc. So we were able to pull out the aerodynamic coefficients, ground reaction forces, stability derivatives, even model rotor wash effects as well. So moving to JSP Sim, now we wanted to leverage the JSP Sim airframe definition model and framework, as well as what we had from OpenVSP to generate our digital twin. So on the right, we kind of broke out the major sources of information that go into the JSP Sim model. Again, JSP Sim is pretty well supported. There's a lot of documentation online about how to do this, but it's kind of the breakdown that we came up with. So starting with kind of your metrics. So those are your areas, visual reference points, sorted reference points in the JSP Sim XML definition. Next, we have the mass properties, mass balance. So that's your center of gravity, your moments of inertia, your ground reactions, including spring coefficients, etc. Then we have a flight control section. So basically, you need to do a flight control mapping from PX4 to JSP Sim internally. That can be one-to-one, kind of depends on how you did your aerodynamic analysis. In our case, wanted to be able to sum trims, also how you treat the A-tail, whether you break that out into a rudder and elevator, or if you have that directly modeled. Speaking of the aerodynamic model, we then have the aerodynamic section, which is kind of the bulk of where the OpenVSP work was affected. So we used a coefficient buildup method to model the aerodynamics. So that means we have coefficients relative to the contributing factors for lift, drag, pitch, roll, and yaw. And then the kind of final section that will lead us into our key JSP Sim insight was the propeller and torque modeling. So this was a major finding for us, that one of the core assumptions in the thrust and torque generator in JSP Sim, there's some assumptions built towards larger vehicles, so larger in size and weight than the UAS that we were trying to model. And so using the built-in thrust and torque generator could lead to some instability issues, specifically when simulating vertical flight. So what we did is, because JSP Sim is very extensible, the XML definitions support calculating and applying forces directly. So we were able to model the thrust and torques directly as forces in JSP Sim. So that was able to circumnavigate that torque generator assumption internal to JSP Sim without modifying JSP Sim directly. So we found that to be sufficient and a very helpful thing for us. So now into the what. So the applications going forward. We kind of see two big takeaways from this work thus far. The first is that we were able to implement this solution in a very low power processing environment. So the whole JSP Sim to PX4 interface, additional sensor simulations, all in hardware that's kind of roughly equivalent from a processing perspective to a Raspberry Pi. So we found that to be very powerful for not a lot of required power. The other takeaway here is the ability to create an airframe digital twin. It's extremely powerful. So to have an actual digital twin of the UAS, given a relatively short turnaround time to conduct rare, normal, and non-normal testing. So specifically things like locking up control surfaces, sensor variants, motor failure, weather conditions, all of that testing on a digital twin of the vehicle, we believe will lead to a path for software regulatory compliance for this enhanced level of software testing. So we think that's a really powerful concept. And I've got a demo here to just kind of show this in action. It's a very simple demo. We have Q ground control on the right there. Just a simple VTOL flight plan. On the left, we have the flight gear visual model. So you see the visualization there. That flight gear is running at 30 Hertz, but the JSP Sim on the back end, it's actually simulating the dynamics, is up at 250 Hertz. So one of the things that we found really powerful about this is the ability to interact with the vehicle just like you would as an operator in the field. So from both a training perspective, but also from a tuning and flight planning perspective, since the dynamics of this vehicle are simulated sufficiently close to the real vehicle, you can use this for tuning. So as you see here, going to the tuning tab on Q ground control, tuning in the same way that you would tune the vehicle out in the field. And this is directly applicable and transferable to the vehicle. So we can tune it in the simulator, we can adjust our flight plans accordingly, we can fly everything in the simulator, take those parameters, load it on the real vehicle, and go. And so we found that to be very helpful, especially with the large vehicle class that we have flying here. So kind of talk through most of the flight, but as you can see, we're going to loiter around this waypoint to line us up for approach as I change the perspective. And here we are doing a back transition. It's also helpful to understand in the simulator how long, from a distance perspective, the back transition would take. As the particular vehicle we modeled likes to fly, and so we wanted to have a good understanding of where that back transition would finish. So there, we just completed it. We're over our land waypoint, and we're descending. So again, just a quick demo of that running live. Still going to land here, but we'll go on to the next slide. So kind of all the data that is available in PX4 is extreme. We all are aware of that. There's a ton of data that's available. But now with this solution, there's also the JSP Sim data that is accessible. So in this slide, we have just a sampling of some of the representative JSP Sim data that's available. So we were talking earlier about static margin analysis. This data is extremely powerful in helping us understand what was going on. So we see in the top graph here on the left, that red line is the start back transition. The top graph is the moments that are calculated from JSP Sim. The graph in the middle is JSP Sim's internal representation of the actuator outputs. And the graph in the bottom are just 3 of the forces that JSP Sim resolved. So drag, lift, and weight. So again, in addition to the PX4 data, we found the JSP Sim data to be extremely helpful. And then, as we said before, this is a very high-level presentation. OpenVSP has a whole workshop. We actually have the overview linked in this slide. I encourage you to check out some of these resources. These are a lot of the resources that we used to go and develop this solution and implement it. So could be something really helpful going forward to consider. So at this time, we can move to the Q&A session. And thank you for this.
All right. So Jesse.
Yes.
Are you? I think you're live there. Yep, you're good.
I'm just going to turn off my screen.
Go. All right. So we got a couple questions here. First question. Can you say more about how to think about using this data for regulatory compliance, especially a type certification?
So I think one of the powerful things is with JSP Sim, there's scripting capability. So you can run not just one flight that's very manual and intensive, but large batches of these flights, different flights, different flight conditions to demonstrate time on the software version or time on the hardware version or both. So I think that's just one of many paths that would be helpful for regulatory compliance.
Next question, did we evaluate AirSim?
So yeah, we had taken a look at AirSim. At the time, the openness and extensibility of JSP Sim was kind of what drew us that way. And that there had been some work in that area that we had found. There's absolutely nothing precluding AirSim from being plugged in either instead of JSP Sim or alongside. And that would be something we'd welcome going forward in the future.
Next question is, are there any plans to contribute upstream of the JSP Sim integrations to PX4?
Yeah, so I believe we're working right now with Auterion on getting that code, the JSP Sim to PX4 code released. I think a lot of these resources will help kind of point in that direction. So even without the direct source code, as we work through that timing process, I think that bridge is relatively accessible, even from the content we've provided here.
Next, and we'll use this as the last question. What's the advantage of using JSP Sim instead of Gazebo?
Yeah, so the 6 degree of freedom model, basically with JSP Sim, we found to have some advantages over the way the physics are implemented in Gazebo. So nothing precluding adding those elements to Gazebo, but since JSP Sim kind of already has that view of the world built in, specifically with fixed wing flight, not only with fixed wing flight, but if you look at what JSP Sim's traditionally been used for, having a large VTOL and trying to tune fixed wing dynamics, JSP Sim kind of lends itself to that. Gazebo could be dropped in. I know, especially with the integrations with Ross and just the community that's around Gazebo. That's why we mentioned it before. would also be a good solution either alongside or potentially in place of. But we found JSP to be more attractive for the digital twin component of what we were looking for.
Great. So I think we're up on time. We'll look to answer any of the other questions online as possible. Thanks, Ramon.
Thanks.
All right, can you guys hear me okay? These guys are the real deal, right? Matt, Jesse, thank you for your amazing presentation. I'll talk to you soon and I'll see you on Slack. Next up, we got Flying into Virtual, the new reality for aerial educational robots by Andrei, Oleg, and Alexei from Copter Express. The returning speakers for 2019, they were one of my favorite sessions last year. I really look forward for the next presentation. They're joining us live from Moscow, Russia. Quick reminder, we have more pre-recorded videos coming up right now. They're premiering right now as we speak. The speakers are right there answering your questions. Please head there. Don't forget to follow us on social media and stay tuned for more. Please don't move. Let me load your next speaker. Hey everyone, we're ready to start with the next session. Let me just figure this out real quick. I'm here. Can you guys hear me? Can you see me? Nice. All right, so the next session is Flying into Virtual, the New Reality for Aerial Educational Robotics. It's by Andrei Kordigotsky, Oleg Flagship, Alexei Rogachevsky, and they're calling in from Moscow. Teamcopter Express is a development and manufacturing company of open source, and the company's quadcopters are designed for educational purposes. Autonomous serving and also aerial parcel delivery. So in 2019, over 1,600 Clover drones were sold worldwide. The last year at the Dev Summit, they presented PX4 in STEM education, how we taught 1,000 students to program with drones. And this year they're back with an update into Flying into Virtual. All right, guys, let me just switch to your screen. You're here.
Okay.
Can you do a quick mic check before I let you go?
Yes.
Hello.
Hello.
Hi.
We can all hear you. Hi. All right, go ahead, guys. Thank you.
Okay, thank you, Ramon.
Thank you.
My name is Andrei Krigotsky. I'm CTO of Copter Express. In Copter Express, we are focusing on the drone education. And today we will tell you how we adapted our educational products and activities to the new reality of education during the lockdowns. During the session, I and my colleagues will briefly describe our platform and educational activities, discuss new challenges that educational robotics face now, and then my colleagues will discuss in detail the simulation environment that we use based on Gazebo and how we deliver it to our students. Our main product is an educational drone kit called Clever. It's a kit with PX4 Autopilot and Raspberry Pi, which we ship disassembled as a set of parts and used to teach students in school, colleges, and universities how to assemble the drone, how to fly it, and how to program it to perform different autonomous tasks without remote control, like locating some objects, grabbing it, replacing, moving to other location, etc. We presented our platform in detail during the previous PX4 Summit. You can check out the video from previous summit if you are interested in details. The idea of our platform is to lower the barrier of entry into the field of flying robotics, to make it really open, both open source and not too complicated to understand for students without heavy robotics background. You can just take our kit, assemble it, insert a micro SD card with our image and take off with just one line of code. Even if you don't know what SSH is, you still can use Clever's web interactive shell. That's how awesome Clever is. All that you can see here on the video is performed on our software platform. It is open source and you don't need to buy it to use. You can assemble virtually any drone with PX4 Autopilot and Raspberry Pi companion computer and flash a micro SD card of Raspberry Pi with our image and you are good to go. You can fly autonomously with just one line of code. If you want to use different companion computer, you always can just get our ROS nodes, which are open source, and use it on your setup. This is a really popular product in Russia, and now we're expanding worldwide. So the Clever platform is used all over the world, and I think it's by far the largest PX4 educational product because it's being used by more than 10,000 students to teach how to make drones. All of videos which I shown were pre-lockdown videos. And of course, lockdowns affected education heavily all over the world. Just a few months ago, online education was, although quite common, still something unusual. And now it's a new standard. In a flash, everything went virtual. Our job is to gather the most of the positive impact of the events which is happening. Robotics education always were in person, because of course robotics is about robots and you need to physically interact with your robot. So this is really a challenge for robotics education, and we will today talk about how we address this challenge. Stage 0 of our response is online video lectures, both pre-recorded and live lectures, but that's what many have used before anyway, so it's not really new. And you can't address main challenge, necessity of interaction with the robot. Theory is good, but robotics education needs a lot of practice. We used simulation before, but it was never our priority because there are so many things which could be improved in Clever platform to make it better. But when lockdowns begin, we made it our priority and started to develop our simulation environment very, very effectively. And now my colleague, our lead developer, Oleg Kalachev, will talk about our simulation. Oleg, please.
Thank you. Okay, you see the presentation? Do you
Yes.
see the presentation? Okay.
Yes.
So here is Gazebo simulation. We created a pretty detailed model of our drone, and you can see it on the picture. And we put a Mavlink plugin and flight controller sensors plugin to it so it can interact with PX4 instance. Of course, we're not taking any credit of creating the interface between PX4 and Gazebo. We just based on the existing standard PX4 Gazebo simulator, but we only modified it a little bit and added some features we need. So although this work is pretty much under construction now, but it's already used in our educational process, and I will show you what it can do. So our goal is to completely recreate the Clover API, the ROS Clover API accessible to the user through ROS services and ROS topics. It includes PX4 itself through MavROS, our autonomous flights API, which we presented last year, all installed sensors API, camera and rangefinder, our LED strip API, and the rest. For example, web video server for monitoring ROS images topics with the browser. So I will not be risking too much and be showing you the simulation live. So I show you some pre-recorded screencasts. So here you see the simulator running in a virtual machine on a Mac, and I use Python to make the drone fly autonomously using the same commands as on a real drone. So before I entered the standard Clover program header from the documentation, and now I use ROS navigate service for taking off, and the virtual drone takes off. And here you see the simulated camera topic, and the drone now hovers stable using our own ROS-based optical flow as on a real drone. So there is no GPS or any other positioning system. Now I ask the drone to fly forward 2 meters using body-related TF frame. And of course, I can ask it to fly 2 meters backwards. And for example, use the very simple land service that just make it land. Also, another sensor available on a Clover drone is the rangefinder. We use a popular STM rangefinder, and we configured a Gazebo plugin to simulate it completely, including the ranging noise. And here is another demo. I fly upwards and downwards on a simulated Clover drone, and I monitor the range value from a ROS topic using the standard ROS plotter. All of the data from the rangefinder, of course, should be also used from the user program the same way as in the real life. Another important feature of the Clover platform is Aruka markers recognition. Of course, we do it in the simulator as well. So here is the demo. The drone sees an Aruka marker, and then I ask it to fly 1 meter above it using Aruka underline 100 TF frame, and the drone hovers, and then I ask it to land to the marker, and the drone do it. Often we use maps of markers to position the drone precisely and without any drift. We pass this information about the drone position in the map using vision position estimate message and how it works, and that's what it looks in the simulator. You can watch the marker map recognition debug topic, and here I ask the drone to fly to some different positions in the marker maps, for example, 3, 3 here, and then I ask the drone to fly to the point 1, 3, and everything is can be debugged in Aruka map topic, and then, as always, I landed the drone. We also install an LED strip to all our Clover drones to make their flights much more spectacular. And we created a Gazebo plugin that completely simulates the ROS API of our LED strip. This allows the user to set different effects to the LED strip, like this rainbow, for example, or I set another effect, wipe to the red color, and you see the red color. Then I set, for example, a blinking effect, and it also works. So all of this works during a flight of a drone. And of course, setting individual LED is also possible with this API. So this API is actually pretty powerful. By the way, if you're interested, this API is documented and open sourced, and you can use it with any compatible LED strip, even without our kit or without our full software package. Also, we can add different models to the world, like these, for example, lines or color circle or something like this, to make some interesting and fun computer vision tasks. And here's another little example of programming a simulator. So now the simulated drone and the real drone does flip, and you can somehow compare how it happens. So we develop everything that I showed you in the main Clover repository, but since it's under development, the work goes in a Clover description branch. So you can check it out if you want. And now Alexei will tell you about how we deliver this to our users. So Alexei?
Yes, thank you, Oleg. So my part of the talk is about delivering the simulation environment to our users. I will tell you about the challenges we've faced and the solutions we've explored. So first of all, let's talk about users. A typical robotics engineer familiar with ROS will probably have a Linux-based system running natively on their hardware, or will at the very least have a virtual machine with their favorite distribution installed and configured. They know ROS simulations may be quite demanding, and thus will probably have a reasonably powerful workstation. They may even know their way around Docker, Rocker, or other container software. And they probably are very familiar with Gazebo, know how to debug their configuration problems, and how to build their own worlds. By contrast, our users are typically those who are only starting their wonderful journey into the world of robotics. They typically have Windows as their primary operating system, with mission-critical software that makes installing other systems not an option. They may be using hardware at their schools or colleges, which is not always as high-end as they'd like. They don't have any experience running Docker or virtualization software and don't really know their way around Linux, In fact, Clover might be their first Linux platform. Our goal is to make their first steps into robotics as painless as possible. So how do we make the simulation environment accessible then? We have several options, each with its own pros and cons. First of all, we may ask users to install Linux on their hardware. This has the obvious benefit of using native hardware and storing the data and software locally. But this is time-consuming and error-prone if done manually. There's also the issue of Linux hardware support, which is not ideal. Each installation would possibly differ, would have its own quirks, and dealing with those quirks may require a substantial amount of Linux knowledge. Then there's Docker, which has been a go-to solution for application deployment for years now. Docker installation is simple, and running a container is a single line in your favorite shell interpreter. But all of that comes with a cost. Since we want GPU acceleration for computer vision, we need to use a native Linux installation. What's even worse is that running a container with GPU support is vendor dependent. That is somewhat solved by wrappers like Rocker, but the experience of running desktop software from a container has so far proven to be less than ideal. There's also the issue of container isolation, which, while generally considered a good thing, may make some tasks like editing files challenging to newcomers. There are also cloud-based solutions, like ROS Development Studio from the Construct. This is probably the most user-friendly option, requiring nothing more than a modern browser. There are several issues with that, though. First of all, there are no readily available open-source solutions. We'd have to put additional engineering resources into developing and maintaining our own system. Then there are additional costs for our customers and possibly for us as well. Hosting would also be a problem, since there are not as many GPU-equipped data centers around the world, and using a high-latency server is an unpleasant user experience. Finally, there's less control over what actually happens on the hardware, much more magic, which, in our opinion, is not a nice thing for an educational product. Finally, there are virtual machines. They are easy to deploy. They may usually be sent as a single archive. All changes that are made to the VM are local. A user may inspect the machine, interact with it as if it was a real one, but with lower risks of data loss. We can pre-configure our machines to have optimized defaults, and best of all, there's no need to change your main operating system. There are still drawbacks, though. A virtual machine requires additional software, such as a hypervisor, and will not perform as well as the native solution. GPU virtualization is not perfect as well, which is a pain point for us. So our solution for now is actually to use a virtual machine. We need a hypervisor that supports multiple host platforms that provide GPU acceleration. It should also be free, at least for personal use. The two options that we've found so far is Oracle VirtualBox and VMware Player. So first, we've tried VirtualBox, but its issues such as rendering errors and overall unsatisfactory performance have prevented us from using it. And so we come to VMware Player. VMware Player is another free for personal use hypervisor. Sadly, it does not support macOS, which makes the users buy licenses for VMware Fusion or Workstation. Other issues are not present, though. The driver for virtualized GPU is built into Mesa. Guest tools are packaged for Ubuntu. There are still some issues with Gazebo that force us to limit virtualized GPU to OpenGL 2.1, but we hope that this will change soon. As such, VMware Player is our hypervisor of choice for now. We strongly believe builds should not be done manually, so we're using HashiCorp's Packer to automate our virtual machine builds. We use VirtualBox to build the VM and export it as an OVA archive. This archive can be imported into VMware, and with some OVF tweaking, we can make the VM with reasonable default parameters. Current build scripts are available in our repository, and the resulting image is available for download. As for the contents, well, all X demos were performed in the simulation environment with minimal customization. And the very same image is being used as we speak for our courses. So that's it from me. Andrei, take it from here.
I don't hear you, Andrei.
Hello.
Yeah.
Yeah. Great. So we rely really heavily on the simulation now, and it is stage 1 of our solution to the education during the lockdowns. We use simulation during the courses, both for students and for teachers. For example, on this slide, you can see the execution of the task when the student should have take from one cube and land on another, recognizing it using computer vision. Yeah, so we use simulation really heavily now, and it's really helps. But it's not everything. Because the world is much more complex, and despite all our efforts, simulated world differs widely from ours. So when our students can run their programs in the simulated environment successfully, we still need to somehow test them using real drones. But all of our educational institutions are closed, so we need to use remote controlled drones. So we use the controlled environment either in our office or in some other educational institution in which our employees or another tutors facilitate the running of the test programs on the drones. So the drone can fly in some environment in our office, while the person who wrote the program is in many kilometers away. We use it for courses, and we are now preparing course in English with simulation and with usage of real-world drones, which are remote controlled. You can check it out on our Square website, and you are also welcome to check out our preliminary Kickstarter campaign. The link is below. So on this video, you can see how the person competing in the drone competition, which was just 2 months ago, controls the drone remotely, and the drone can perform some task in real world using the program which was created by many kilometers away. Yeah, and here on another video, you can see another competition when guys programmed the drone to fly autonomously using the Clever platform. You can see the debug screens here. Yeah, so they used OpenCV to program the drone flight, autonomous flight using the Clever platform, and then run them remotely. So our solution to the education during the lockdowns are online lectures, simulation, and remote controlled drones. So yes, lockdowns are bad thing overall, and the pandemic is of course bad, but we need to get the most of the good part of it, because it really catalyzes the transformation, the going to virtual, and so we can use it to push virtual education, to push using of simulation and other different modern techniques to educational institutions, which are usually quite conservative and want to have real lessons on site and are quite closed for new modern things. So use this moment to get it. Use our open source platform. We are very glad when everyone use it, and good luck with your educational projects. We are open for any questions. Yeah, 1 second.
Okay, so Ramon, will you read them or? Okay, can we replace remote control with mobile operating using an UDP port for indoor use? Can we?
Well,
I mean, So you mean to operate the drone from away using UDP? I mean, not locally, but remotely. I think it's possible, but the ping would be very big. Maybe 5G will help with this. So, anyone?
Thank you.
Do you want to tell something about this?
Yeah, the next question is, can we use OpenCV or other object detection libraries? And yes, of course you can, and it's part of our curriculum. So we even teach how to use OpenCV with our libraries and our ROS nodes. But you can use whatever you want. If it works smoothly with ROS, it's great because our simple of board node is ROS node and you can communicate very smoothly. But you can use virtually anything that will run on your companion computer with our ROS packages to perform some autonomous tasks using object detection libraries. Yes, we create the platform exactly for use cases like this.
And the third question is for Alexei, I think. Alexei.
Well, any plans to support ROS2 in the future? Well, I guess it depends on your definition of future. For now, we are on ROS Melodic and are transitioning to ROS Noetic, the last ROS1 release. Well, eventually we, of course, we will have to transition to ROS2, and we will probably embrace this transition as well. I'm personally really excited about that and about the PX4 and ROS2 integration, but that's, I guess, not in any concrete plans right now.
Okay, I can read the fourth question. Is there a gap between simulation and reality? What challenges did you face running simulated code? I mean, I think it's if there is some simple task like flying from one point to another, there's almost no difference because the simulation works pretty good in this task. For example, if you're working on very complicated computer vision problems, then the rendered 3D world can differ from the real world. But this is still useful, I think.
Yeah, I think I'll probably talk about it a bit more. Well, sometimes you tend to bump into some of the simulation quirks, like Gazebo not actually Gazebo sensors not providing you your sensors with a constant update rate, but rather giving you an option to provide a highest bound for your simulated sensor. So in case of cameras, if you for some reason don't have a GPU acceleration on your system, and you want to place a camera that's you would want to provide like to publish an image 30 times per second, there can be issues when the most that your hardware can do is actually 5 times per second, and for some reason Gazebo will not always slow the simulation down. So there's that.
Awesome. Thank you guys. Thanks a lot for your
I think
help
maybe
today.
we should ask Svetlana for something to tell about her experience, because I think she should say something. So what's your experience about remote competitions?
Thanks for your question, Oleg. My experience, it was very interesting for me and for our team. because we don't have any students locally in our office where we make a remote controlled launch of the drones. But it was a very strange experience because we create system control without manual control, only autonomous flight, only using codes from our students, and they need to give more information from each flight at the polygon in our competition. It's good opportunities in our current time with pandemic. And also, I saw a question about using LTE or EKF. We use both LTE or EKF too.
Okay, Oleg could answer this question, but I really think our time is up. Yeah.
Yeah. Hey guys,
So-
sorry to cut you out, but our time is up. Our next speakers are waiting. Thank you.
Thank you.
Multicopter Express.
Thank you. Very pleased.
Yeah.
See you soon. All right. Hey guys, I'm back. Can you guys hear me okay? Yes, audio levels are good. Guess what? We're still live. So I'm back. I'm Ramon Roche. I'm the program manager for Dronecode. We just heard from Copter Express. Thank you guys. That was great. I really look forward for those slides with all those resources in them. I will share them via Sket soon. Guess what? Next up, we got Overview of Multicopter Control from Sensors to Motors by Matthew Brascani and Matthias Grob from Autherian. They're also returning speakers from 2019. They're members of the PX4 Dev team, and they're joining live from Zurich, Switzerland. Give me a moment while I connect with them. I'll promise it won't take that long. Be right back. All right, so we're running a little bit behind schedule here, but I'm going to try to catch up real quick. Our next session is Overview of Multicopter Control from Sensors to Motors by Matthew Brascani and Matthias Grob. They're coming from Zurich, Switzerland. Matthew and Matthias are both flight control engineers out of Autherian and are PX4 maintainers. In this session, they will give an overview of the components within PX4 to control multicopter vehicles from sensor input pipeline overestimation through cascaded position, attitude, rate control, and the output allocation, and also zoom in on certain selected aspects and answer additional related questions regarding navigation, controls, and development. All right, so let's hear it from Mathieu and Matthias.
Welcome to a new talk about in the navigation control series. I'll present today with Matthias the overview of multicopter control from sensor to motors. So I'll first let Matthias introduce himself.
I'm Matthias Grob, Mattuger on GitHub. I work with PX4 for a lot of years now. I joined the maintenance and developer team in 2017, and I'm flight control engineer at Otarian.
So my name is Mathieu Bresciani. My GitHub nickname is Bresh. I'm maintainer since 2018. I worked for 3 years with PX4, and my main focus is estimation and multicopter control. So we'll first give you an overview of the multicopter pipeline, then specifically on the IMU side of that pipeline, different paths on estimation and control. Then Matthias will give you an overview, an update on flight task from last year, and then explain the quaternion attitude control. And I finally talk about control location.
So like the title says, we want to give you a quick overview over the components in PX4 that make up everything that's necessary to fly a multicopter. This overview is very rough, and there's not an arrow for each and every data path, but the general path is there. So from left to right, we have the feedback loop here. Here closed, and from the top comes the data path that determines the behavior of the vehicle. So on the left, we start with sensor drivers that get in our raw data from an example of sensors. For every component, I wrote down the path as well in the code if you want to look it up such that you will easily find it. And I wrote down the topics that are published over UORB, where the data is then given over to the next module. Each sensor publishes his specific data on a specific topic, and this then gets further processed in the sensor hub that we'll cover later on a bit more. Then it goes through an EKF, the estimator, which is covered by Paul Riceborough tomorrow. Then from the top comes, as I said, the behavioral path of data. So your input comes through here, what mode you're in, how you want to fly, and what your stick input is from the remote. And this goes then into the position control, attitude control, and rate control pipeline for multicopter that was covered by Anton just before. And we will cover some, like we said, some of the flight task updates and attitude control in this talk. Then it goes through the mixer to determine what motor needs to do what. And there's also a further talk about control allocation later on in the Dev Summit.
So first part, what I would like to talk is the IMU pipeline. So I would like to emphasize that there are two different paths. There is the top one, which will go for the estimation. So we have that path that is low rate and unfiltered that goes directly to the EKF2 after coming from the IMU driver. And that is the low one, which is a high rate and filtered signal that goes to the rate controller. So first we have the driver directly reading the data from the IMU. That one is usually triggered by an interrupt. And then you have processed the accelerometer on the top here and the gyro on the bottom, quite similarly, except that on the accelerometer side you have a clip counter that then is used by the EKF to try to counteract some effect of clipping. And then there is the rotation to put everything in the correct frame from the defined autopilot. Then it gets integrated to have the defined rate of here 800 Hertz, which can be also selected by this parameter that controls mainly the gyro rate frequency. So it can be changed from 400 to 4 kilohertz. Not that you need a quite new generation of boards to run the control at 4 kilohertz, as it consumes quite a lot of resources. Default is 800 hertz. And you can log directly here the FIFO data at 4 kilohertz if you have a good SD card by enabling the logging with that parameter. And then you can directly plot those spectrogram and fast Fourier transform of the accelerometer and the gyro using that website, which is Flight Review. And so you can analyze the vibration of your drone quite well. Sorry for that. So then the estimation path, which was on the top of the slide before, you can select the IMU integration rate that will define the output rate of the EKF, which is the attitude message, but not the other one, which is position and velocity, and the other message which are fixed at 100 hertz. So there are two, for each IMU, you have one of those blocks, which is vehicle IMU, that receive calibration, compute some vibration metrics, and are published to the vehicle IMU topic. That vehicle IMU topic, so as I said, there is one per IMU, and that will enable us in the future to run one EKF per IMU and then switch over. Right now, we're still using that topic that you might have heard of, which is called sensor combine. It's actually one instance of that vehicle IMU topic with the highest priority. So soon we'll have multi-EKF. We already have prototype working, and that will enable switching between IMUs depending on the state of the estimator. Then on the control path, which is faster, we have first part the acceleration. So it got also calibrated, compensated for the estimated bias of the estimator. And then there is a low pass filter that you can select, which is that one, IMU XL cutoff. And that goes into the vehicle acceleration topics. It's not a lot used in Multicopter, but it's more used on fixed wing and also on in Commander for launch detection and load factor computations. Here on the bottom part, you have the gyroscope. The data that comes in gets calibrated, also compensated for bias from the estimator. And the difference with the accelerometer is that you can select here a notch filter and then the low pass filter. Also in that same block, it computes the derivative and filters it. That will go to the rate control directly. And on the right side, you see all the parameters that can control the different kind of filters. And on the bottom here, like that specific notch filter, where you can select the notch frequency and the bandwidth of the filter.
So since I'm one of the authors of Flight Task and I gave a speak already on the last year's Dev Summit, I wanted to give a quick update on the to-dos we had from last year, what was done in that year. One of the to-dos was to avoid discontinuities between mode switches or also then task switches, which were present because the new task didn't know what the old task was doing before and only had the current vehicle state to take over, which is not enough because it cannot know how to continue with the set point in a continuous way. And the idea here to solve that is to just capture the last set point that was executed from the task before, and that gets passed onto the activate function of the new task, and then it's his responsibility to take over continuously. A second bigger change that is now made possible is the execution of acceleration set points, and I have the next two slides to explain this in more depth to you. So like presented last year, the main interface between flight task and position control was position, velocity, and thrust. And now new, the thrust, the unit thrust 3D vector is replaced with acceleration in actual meters per second squared. This is done because the unit thrust was more dependent on the vehicle mass and maximum thrust. And so you can now set in your flight task any set point combination of position, velocity, acceleration, yaw, and yaw speed, but only adhering to the two requirements I wrote here. Every dimension needs to have at least one set point, otherwise it doesn't know what to do. And the horizontal set point in X and Y needs to come in pairs, so you cannot exclusively have position set point for X and velocity set point for Y, for example. As an implication of that, the output of the velocity controller is now not thrust, but acceleration. And to have that represented in the gain, we rescaled the gain from and renamed the parameter with that underscore x at the end. And to show you how to convert to that new gain scaling, the default gains were rescaled by this factor of the gravity acceleration over hover thrust, which is approximately 10 meters per second squared over an assumed 50% hover thrust, which is about 20, factor of 20. So if you rescale your gains, you will have acceptable results, and from there on it should be more consistent independent of the vehicle weight. Additionally, I want to show you that the strategy of the attitude set point generation changed. Before, the 3D thrust vector was directly used to generate the attitude, and that had some problems because the vertical vehicle dynamics are usually much faster than the horizontal or rotational ones in practice. And so the idea to solve this is to make the tilt of the vehicle, so the tilt of the attitude, independent of the vertical demanded acceleration. I have here a small example on the right side. We demand a horizontal acceleration of 4 meters per second squared, and that directly determines the tilt of the demanded thrust by projecting with assuming the gravitational acceleration in the vertical direction. And the demanded acceleration in the vertical direction then can only change the amount of collective thrust, but the tilt stays the same independent of the vertical control. Further, I want to address some to-dos that are still remaining related to flight tasks. Flight tasks are now a library instantiated in position control and should be moved out into their separate component. There is still an inheritance structure which is kind of hard to get into, and it hinders the sequential reading of what is executed. Then flight tasks are planned to be extended to flight modes, which support also other set points like rate and attitude set points directly. This would then cover all possible flight modes, and we have no exceptions left for modes that cannot be covered. Then a goal is to import the existing navigation states for autonomous flight, like takeoff, RTL, land, into such flight modes, such that we have one single type to represent the mode and not like scattered over the code. Then there's also a low barrier with those flight modes to also be used for other vehicle types like fixed wing, VTOL, or rover. And also a further goal is to hook it up with the state machine, which is now Commander, to be able to infer the state machine transitions from certain properties of the mode directly. Now I want to go further down the pipeline to the attitude control. I want to explain, hopefully in an easy way, how we calculate and act on an error in attitude. So in green on the right side, we see our desired attitude set point, represented now here as a completely level attitude with these 3 unit vectors. Then we know from the estimator in red that we are currently tilted to the side, and so we need to roll back. In quaternion arithmetic, a multiplication is a rotation of a quaternion. So we are looking for the error that rotates us from the current estimate to where we want to be, the set point. That quaternion error we find by rearranging the equation. Then after we calculated this quaternion error, we take a closer look at the individual 4 components. The first component, which is the first line here, we are not interested in this calculation. So we look at the other 3 components that are at the bottom, and they represent a 3D vector which points into the direction of the rotation axis around which we need to rotate. It's the blue vector here in the graph. And this vector is scaled by sine of the tilt angle divided by 2. I quickly plotted here sine of alpha divided by 2, and we can see between minus 180 degrees and 180 degrees, it's monotonically increasing, which means the more tilt angle we have, the more error we infer, and the more action we give as a rate set point. And so we take these 3 components at the bottom to use as our rate set point, of course scaled by the proportional gain of the controller. I didn't invent this algorithm. It's represented more in detail in that paper that is also referenced in the code.
So I'll quickly discuss about control allocation. So basically what's control allocation is a way to transform the desired force and torques that come out of the rate controller into the actuator outputs. So it's kind of mysterious blocks here that has to do that operation. Fortunately, we can use linear algebra to achieve that, as the system is close to linear if we only use force and torques. And how do we compute that control allocation matrix? So what we do is that we take the geometry of the vehicle and the force that can produce each motor. Given that, we can build the actuator effectiveness matrix here. And then by computing the inverse, we can have the control allocation matrix. That inverse is, if it's squared, it's just a squared matrix, it's just a normal inverse. And if not, if you have more actuators than inputs, then you can have a pseudo-inverse here computed by a Moore-Penrose solution. So basically how to add new geometry. So you have a new vehicle that has a crazy shape with 20 motors, or I don't know how many. You want to add a new file for that, to have a new mixer. You can have the description, you can have your own description in a new file in that path. It's a TOML file. You can describe the position and the force of each actuator. You create a new key for it, a unique key. And then in the ROMFS, you can create a new mixer with that line, which means that the R is for a multicopter. Here is your key. And those numbers are just for legacy reasons. You don't need to worry about it. And then simply call that mixer, that your new mixer, into your config. And at build time, it will compile everything for you. We have a Python script that will generate directly that control allocation matrix based on the geometry, generate the C file, and it's ready to go. Also, that's why it's super fast to run in R, because you don't need to recompute every time. One option that you can enable in control location is called air mode. So air mode is a way to increase the authority of some axis over the thrust. So for example, here on that graph, you see on the x-axis, that's the roll torque you're demanding on with that small arrow here. And on the vertical axis is the collective thrust. So for a normal quad, it looks like that shape. So you have the maximum authority when you're at 50%, because that's when you have the maximum differential thrust that you can apply. So if you have no air mode and you can attain the desired torque and thrust, it will just allocate it. If you have air mode, it's the same. Here, if it's unattainable and you have no air mode and the roll torque is not feasible, then it will constrain it to the what's actually feasible and not touch the thrust. If you enable air mode, what you can have is that it will give you a boost of collective thrust to be able to allocate the full torque. So a few things to mention here. So you can activate it by setting that MC air mode parameter. You have different modes, so a roll pitch only, prioritization over thrust, or roll pitch yaw. You will only activate normally roll pitch yaw on a racer or on drones that have strong yaw authority. And it works much better if you have kind of a linear mapping between the output that goes to the motor and the actual thrust, because we assume it's a linear system. So try to linearize that mapping using that model factor here. And also be sure that you first tune your vehicle before you activate air mode, because otherwise you can have a bad thing happening. Let's imagine you have here the x-axis that oscillate. If you have air mode active, it will always put your thrust at the midpoint. So you might fly away because of that. And thank you for your attention. Now we'll answer a few questions. So yeah, I'll directly take the first one. What is accelerometer clipping? So basically, clipping or asymmetric railing is a problem that you have on the z-axis, so on the vertical axis of the accelerometer, because of the gravity offset. So the problem when you start to have high vibration, you have clipping on both sides, and the actual average value will be 0 instead of 1G. So that will fool usually the navigation inertial solution of the estimator, and as a result, the vehicle will fly in the sky usually. So we implement something to detect that clipping, and then to constrain the estimator not to drift because of that.
So I take the next question. The question is, are acceleration set points available in the last stable version of version 1.10.1? And the answer is yes, it's available for the interface of the flight task. At the moment, I think there is no flight task directly using it for other things than feed forward. So the current mission and also stick mapped flight task for position mode use it as feed forward, and it's used for certain specific things like VTOL transition, but there is nothing that takes advantage of the exclusive acceleration set point. But that can be added at any time and will be added. The next question I take as well, is there an up-to-date tutorial or summary that covers everything to create a new flight task? If not, can we expect one sometimes? And I can say it's a bit of my fault, because in the dev guide you will not find the content of last year's flight task talk, except for the video of the last talk. And I will still add the content, so the graphs and the description, yes. And we will also add the content of this talk such that you're able to look this up later on. Like the video will be available, but also in the dev guide. So the next question is, will the plan for flight task structure improvement be implemented in version 1.11 stable version? I would say that depends on what improvement. Like, I named a lot of improvements, six possible ones. And I think the first 3 ones were lower hanging fruits that will be done a lot earlier and can probably be expected for a next stable release, but I cannot promise anything. And the ones on the bottom are more in-depth and will probably take a bit more time.
Okay. No more?
Thank you. Can you guys hear me?
Bye.
Wow. Thank you guys. That was super cool. Guess what? We're back. We're still live. Just a quick reminder, we're still live. There might be more quirks coming along the way. We hope they're not as intrusive and that you remain with us. Welcome to the PX4 Developer Summit. I'm Ramon Roche. I'm the program manager for Dronecode. I'm calling in from Tijuana, Mexico. Really happy to have all of you here. Thank you, Mathieu. I think a lot of the community members are really excited right now. That was a super informative talk. Great job. All right, so next up we got Embedded Machine Learning in Practice by Alessandro Barnde from ARM. He's the IoT ecosystem manager for ARM, and he's going to be calling in from Cambridge, UK. All right, give me one moment while I connect you to the speaker. Hey, we're back. Thank you. Now we have Alessandro Grande. He's the IoT ecosystem manager for ARM, and he's calling in from Cambridge, UK. He's going to be talking to us about TinyML and doing machine learning. Let's see, how does that relate to drones? Wait, let me show you.
I can't see
There you
myself, so
go.
I'm not sure. Am I on?
Yes, you're on.
Oh, hey. Hi,
Go
everyone.
ahead. The mic's all yours. Thank you, Alessandro.
Thank you. So I'm going to share my screen. Just give me 1 second. Okay. Cool. So thank you for having me, Ramon. And I'm really happy to be here today and be able to share with you my passion around machine learning on embedded devices. So as Ramon said, I'm a developer advocate and ecosystem manager, and I work for ARM. And let's see if this works, this slide. Okay, yeah. And why am I here? Well, the interesting thing is that because of my job, I'm exposed to a lot of really interesting people and a lot of interesting trends that I see across the industry. And with this comes a lot of use cases that people and industry leaders are actually trying to make a reality. The other point is that I'm passionate about machine learning, especially on embedded devices and the capabilities that this unlocks. I want to share also with you what I've learned in the last couple of years around machine learning on embedded devices and this new world of possibilities that's opening up. So I guess I'm coming from an IoT space, right? So why am I here and why am I talking to you about machine learning on drones in some ways? I think really when we look at the challenges in drones, they're very similar to some of the challenges that we see in other spaces like IoT, for example, or robotics. And these are that we are in a situation where real time is a really important thing, and we have to make sure that we are making decisions in real time. And the other thing is that the devices that we're operating with or we're using are situated in a very energy constrained environment. You usually are running off batteries. Obviously, you want to try and fly as much as you can, and this enables you to, you have to make sure that you are considering that when you're looking at what's running on your device. The other thing is that you are in a constrained memory system, like in a lot of IoT devices. And last, you've got actually a lot of data coming from a lot of different sensors, and you want to make sense of this data. So I really see, in the same way as in the IoT world, I see a massive opportunity here. And that is really embedded machine learning, or how some people like to call it, TinyML. And what is it actually? What do we mean by embedded machine learning or endpoint AI or TinyML? It's actually machine learning that can run on devices with an energy cost below a few milliwatts or around a few milliwatts. What's interesting is that most of you are probably familiar with machine learning, so I'm not going to focus too much on what machine learning is. But one thing I do want to mention is that this can be mind-blowing to some of you. It can seem mind-blowing because actually we used to think of machine learning running on big GPUs or big servers, but actually there are two steps in machine learning. One is the training, and for that you actually need a lot of data, a lot of compute. But then there is also the other side, the inference side, that is basically making sense of the data around you and actually taking actions on them. And that actually can run very effectively on smaller devices, as we will see today. So what are some of the benefits of actually thinking about machine learning on embedded devices? I like to think that there is actually three main ones. One is security and privacy. And why is that a benefit? Well, because think about the fact that every time you shift data and you send it somewhere off chip or somewhere else, potentially on a cloud or on a ground station, in a drone situation, what you're doing is actually sharing that data with someone else or some other entity. Where if you're able to do the processing on the device, you're not sharing that data with anyone. You're keeping it privately on the device. The other really efficient thing that I like to think about when I think about machine learning on embedded devices is actually power and cost. Moving and fetching data is very expensive, and if you're sending data outside of your device, that cost increasingly increases massively. And therefore, the closer you do the processing to the data itself, to where the data is captured, the more efficient and cost-effective it is. The last point is actually reliability. I mentioned before, obviously, in a real-time situation, you want to make sure that what you're doing is actually happening right away, and actually you don't want to be making decisions delayed from what you're doing. So, for example, if you're trying to do object detection to object avoidance, you want to make sure that you avoid your object in time before you hit the object. So you have to make decisions right away, and you know this better than me. And actually being able to do this, taking these decisions closer to the data itself, to the sensor itself, being able to do machine learning on the sensor itself potentially can enable you to do it even quicker. Now, there are a lot of use cases. Everybody talks about machine learning, and it's interesting that actually there is a big range of use cases, starting from GPUs that are really important when it comes to really complex real-time object recognition or person identification. Cortex-A's are the more Linux-enabled devices, ARM devices. Those are able to do a lot of machine learning. Like, for example, Raspberry Pis are able to do computer vision type applications and run very efficiently. But then if we move down the left of this graph, of this table here, we could see how actually there is a lot of use cases that could be covered or could be effectively run on Cortex-M or microcontrollers. So things like vibration detection, sensor fusion, keyword detection, and other things like, for example, person detection. So individually detecting whether a person is in the video or not could be something that could run efficiently on a really small device, constrained device. The other interesting thing is that actually this trend is here to stay, because actually we see that we're coming up with all these different devices, and there's more and more Cortex-M devices being shipped every year. So there's even more chances for all these devices to get into places where they could be utilized more effectively and more efficiently. So I wanted to touch on, when does it make sense to actually do machine learning on endpoint devices? I believe that it makes sense to do machine learning, to think about machine learning on constrained devices when you have data that's messy. So when you're not really sure how to solve your problem, when you probably would struggle to come up with an algorithm, and you're trying to find a solution that's not very well understood yet. So in that case, you could try and see whether a machine learning model could be able to make sense of your data and actually give you results that you want, or make sense of the data and actually help you to take action. So there are different use cases, as we said before. I think it's useful to think about three different use cases categories, and those are really vibration and motion, so any kind of signal outside of voice and vision, and then there is recognition of voice or sound, and images and videos, really. And those are like three different classes of the problem that machine learning could solve on embedded devices. Okay, so now we're moving towards actually the more practical side of the presentation, and in a few moments I'll actually show you a live demo of this happening. So I'm really excited about that. So let's get into the beefier part of the presentation. First of all, I wanted to mention that actually this is a massive ecosystem effort. It's not just one player that's enabling this technology to actually work and to actually be efficient and effective. It's actually an ecosystem of partners. And you can see here, really, there is a lot of partners that are focused on the software side. So algorithms, software tools, RTOS partners, and all other software partners. And then there is the silicon partners, those that are actually building the hardware itself. And it's interesting how all these players are actually coming together to make TinyML a possibility. What does it actually look like? What does the flow look like for a developer? Well, if you're familiar with machine learning, you know that there is a lot of different frameworks out there. One of them is TensorFlow, for example. So if you think about a TensorFlow generated model and trained model, you can then think of taking that model and optimizing it for running on an embedded stack. What you use in this is actually a TensorFlow, a Google version of TensorFlow called TensorFlow Lite Micro, so for microcontrollers. By utilizing this on top of an embedded stack, you can then use your favorite tool like Arduino or Kyle Microvision or Embed Studio to actually generate binary code that can be used on your device itself. So I wanted to take you through some of the steps that are important to keep in mind when you're doing machine learning on these constrained devices. First of all, I think it's important to realize that actually you need to pick your device first. You need to be able to understand that actually, in comparison to classical machine learning, actually here you are on a constrained device. So you really have to know what your device is and what capabilities it has. The next bit is actually you need to be aware that you need to pick a model that's compact enough that could run on this device. And the last point here is that you want to make sure that the model has less operations. Now, there is a stage that's called optimization stage, and this really it boils down to making sure that the model that you've created can run on your device. And to do this, you have to shrink the model somehow. There is different optimization techniques, one of which is, for example, quantization. So through reducing the size of the weights and the weights and the other bits of the model to run on your device, you can reduce the size that it occupies and run more efficiently, effectively. So you're doing operations more quicker because now you're doing it on smaller parts of data. So this is really important. What's interesting here is that actually you can do this without losing any accuracy. The last thing I wanted to show you here is that actually, as I mentioned before, TensorFlow Lite Micro is a tool from Google. It's an inference engine from Google that ARM is partnering with to actually optimize the efficiency of the inference engine itself on ARM hardware. So we're partnering with Google to make sure that actually TensorFlow runs efficiently on ARM. And this is what you utilize to actually do the last bit of the porting to your device. So you generate the C code that then you can run on your device. What's really interesting is that already in less than a year, there's been a lot of different hardware platforms that are supporting TensorFlow, TensorFlow Lite Micro, and are running effectively these models on their hardware. So you can see here a bunch of different examples, and one of them that I'll show you today in action is actually the Arduino board that you can see here. A very interesting little board. So now I wanted to get to the actual action, and I wanted to show you that there is a lot of things that you can do today. And actually here I've got a list of tutorials and resources that you can look at. They're all also listed in the developer.arm.com IoT website. You can find them there, but I'll be sharing this slide so you can take a look at these afterwards as well. And now I wanted to run the demo. So I think I need some help from Ramon on being able to run this. So I'm going to unshare my screen, and I'm going to share another screen. Just give me 1 second. Okay, so we're getting ready. So what I'll show you today is really a simple way to get started on machine learning with your microcontroller in a few easy steps. So let's see here. I'm sharing. Okay, so one of the guides that the Arduino team has put together. A lot of work has gone into this guide from the Arduino team, so props to them for doing this. They've put together this really, really easy to use guide that you can use to train your model and to run it on your device. So I wanted to show you basically something that people that are working in ML are quite familiar with is Jupyter Notebook. This is a tool that allows you to train your model and optimize it on the cloud directly without having to build it on your local hardware. So Google has created the Colab that Arduino is actually using in this example. So you can see here, this is actually. You should be able to see, the different steps. So there's a setup step. There is I've already run all this for just before this presentation. I didn't want to run it now just because I'm conscious of time. But it's really a few simple steps. So you can see here what you do is basically you get your data through your Arduino device. You upload it here on the left, and then you're able to train the model. So you prepare the data set first. And then you randomize it and split it into different sets of data. So you have typically your training set that in this case is 60% of your initial data, 20% of validation, 20% of testing that you will use later to do actually the testing. Then you train the model. This doesn't take too long because it's actually running on the GPU, on a big beefy GPU. And then what you could do here is actually the Arduino team has done a really good job by showing you some of the really interesting data on the loss function, for example, that can give you an idea of how well your model is performing. So you can see here the plot of the loss function in my case. And finally, you can run the test. So to see how it's performing. In my case, for example, I trained two different types of motions, turbulence and up-down motion. I'm trying to simulate, for example, a use case in which I'm trying to understand whether my flying device is actually in turbulence or is perceiving turbulence, or it's actually going up and down. And you can see how the performance of this model is actually really, really good. And then here you can convert. The last stage is converting the trained model to TensorFlow Lite, and at the end you're able to generate a code that can run on Arduino itself. So I'm going to now share the actual. So this is the Arduino code that's running on my device, and Ramon, can you confirm that people can see my camera?
Yes.
Okay, cool. So you should be able to see the Arduino device, and you're seeing now on the camera, on the screen, that by moving this now, I will be able to understand the motion, right? So let's see if this works. Demo gods, please be with me. So let's see. Okay, so if I move up and down, that's up and down, up and down. Let's see if it detects turbulence. Up and down again. And you can see how the accuracy of this is actually quite impressive for being a model that runs on a Cortex M4 in a really, really efficient way. And you can see actually the speed of recognition. I mean, it's actually really fast. The only thing that's slowing it down is that there is a window of data collection that's happening. But you can see how actually it's really good at recognizing whether this is turbulence or up and down. And actually, you can train the same. So you could use the same model here to actually add more classes. So you could potentially train multiple classes to understand multiple types of operations of your device. And obviously, it's taking data from the accelerometer and making sense of that data. And again, data from an accelerometer is usually very messy. And what's interesting is actually this is able to make sense of it without actually much work. I mean, the training here is below a few minutes to be able to do this and get this with this accuracy. So I'm really impressed by the Arduino, the work that Arduino has done, and all this again is running effectively is running on TensorFlow Lite Micro, and it's running in the end optimized on ARM hardware. Okay, so with that, I go back to the slides here. So in summary, I really think that machine learning on constrained devices, TinyML, is actually happening now. So it'd be interesting really to understand all the use cases that could be unlocked in the world of drones. I'd be really curious to understand, the different things that the different places where you think you could utilize this type of machine learning, and really reach out and let's collaborate. I'm excited by what's possible, and I'm really excited to hear from you guys what you guys have in mind and what kind of stuff you think could be done with this type of technology. Last but not least, there is a link here if you want to learn more about the different partners and what they're doing. There is we're running some AI tech talks that you can follow by clicking on that link. Okay, that's all. So I think.
Thank you,
Alessandro. Yeah, we can go to questions.
That was really good. I have a few questions. Do you mind stop sharing your screen? And I'll share those questions via Teams.
Sure.
Awesome. So I'm going to just drop the questions here. Thanks to the volunteers that put them together, and thanks for the community to really help us with those questions. Like, they've been really at it since the morning. Alessandro, so we have a few questions here. Feel free to pick the ones that you two that you like the most. I don't think we have time for more than 2 or 3.
Yeah, I'm just looking at the question. So, okay, so there is, I'll just pick the first 2 to start with. So the first one is, what is the difference between embedded machine learning and running the machine learning in an SoC? So, okay, we're talking about the same thing. It depends how big your SoC is, how capable your SoC is. So if you're thinking about Linux-enabled SoC, like a Raspberry Pi, for example, that has a Linux-enabled SoC, you're usually running more beefier models. What we're talking about here is the ability to run these models down to a few milliwatts of power. So the ability to run these models in very constrained devices, and the ability to do it effectively and efficiently. So that's, I guess, that's the difference. Is, SoCs are there is a wide range of SoCs based on ARM. As I showed a graph at the beginning, there are SoCs that mount different types of CPUs, and what I think is really exciting is the ability to run machine learning on the really tiny SoCs or the really tiny CPUs, the Cortex-M CPUs. So the ones that, I guess, to put it into context of drones, the ones that usually are on the flight controller itself. So the SoC on the flight controller, or SoCs that could be attached to the sensor itself. And I go for the second question as well. Can you train on small devices? So there is some partners that are looking at that and are starting to do some of the training on the devices. Right now, it's probably best if you don't do the training on the device, but you do the training off the prior to the device. And what you could do is feed back some of your data to potentially an external source, so you could refine the model and potentially redeploy a better model in the future. That's the easiest workflow today, but things are moving very fast, and I can see how the training could start happening on device as well. Do I have time for another one? Okay. Sorry, I'm just reading the questions. Okay,
Alessandro,
so yeah. what's the breadth of ML models we can use on embedded systems? Are there only computer vision models, or are there more ML models we can use? For example, SVM for sensor fusion. So the reality, as I mentioned before, is that it really depends on understanding the size of the model, and you know, there are some models that are that have a lot of operations, and those are probably not the best models to run on really tiny devices. But there are a lot of different models that are being ported to the embedded devices right now. I shared some of the links to some links to some guides where you can see a bunch of different models. So some that are running, like the one that I used today, that are running fully connected models for vibration, for example, use cases, or in general sensors like accelerometers and stuff like that. And then there is CNNs that are being utilized a lot in computer vision and other models. So there is a lot of research around trying to port different types of models to embedded devices. And then I'll just go with the last one. Can I run TensorFlow Lite on an NXP MX8 Mini? So TensorFlow Lite can be run on multiple platforms. If you go to the TensorFlow Lite Micro website, there is a list of supported devices, and there is, you know, obviously there are ways of porting that to different platforms. So if it's not ported to the device that you're using today, you can do that. Don't forget that the IMX8, for example, has got multiple CPUs. So some of them will run Linux and will run containers and will run, will give you the ability to run machine learning in a different way. And then there are also Cortex-Ms on there, so you could run potentially TinyML on those Cortex-Ms.
Awesome. Thank you, Alessandro.
Thank you. It was a pleasure.
All right. Hey, guys. Welcome back to the PX4 Developer Summit. Your host here, Ramon Roche. Thanks, folks, for your help with the questions. Team effort, right? Thank you, Alessandro, again. Super cool demo. Please share the link on Slack with all of us. There's a lot of more questions for Alessandro, so maybe you want to join us on Slack and do a live Q&A there. Awesome. Thank you. Sounds good. I'll share the link with you, Alessandro. Bye. All right, so next up we got using PX4 for educational satellites Cansats by Avas Maski. He's calling from Kyushu, Japan. Wow, we've been all over the world today. Yeah. So let's hear from him. What does PF4 have to do with Cubesats again? Confused. Let's see. I want to know. Give me a moment while I connect you to Avas Maski. Hello? Community, we're back. Thank you for waiting. Sorry, I hope that wasn't too long. We're still at the PX4 Developer Summit. Remember, PX4 Autopilot is the #1 open source autopilot. Let us know how this is going. Please share your comments on the chat. Let us know in Slack. We're here waiting for your feedback. I have with me on the line Avas Maski, who's calling from Japan. He's a PhD student at Kyushu Institute of Technology and has been directly involved in 4 different satellite CubeSat projects, placing 7 satellites in orbit. All right, let me change to my live video here. 7 satellites in orbit. This also involved building and launching the first satellite of Nepal, Nepalisat #1. He's interested in camera design for space applications, machine learning for image classification, and is actively working towards educating the next generation of Nepal through hands-on educational satellites called Cansats since Nepal first training in 2016. Wow, that's a mouthful. I'm really excited. Avas, can you still hear me? All right, so let me just switch to you right now.
All right, thank you so much.
You're welcome. Take it away.
Yeah, thank you for that introduction. Looks like I don't have to say much about myself now. Okay, let me just share that screen. Can you see my screen now? All right, okay. Hi, everyone. I am Abbas Maske. I'm currently a PhD student, but I'm also managing a BIRDS 3 satellite project that built the first satellite for Nepal. And today, I'll be also talking about Cubesats, but primarily focused on Cansats. And I'll be discussing about how I've used PX4 for educational satellites called Cansats, and what the state of present and post-pandemic prospects for Cubesat Cansats can be for using drone technology. Okay? So these are the agenda for today. So I'll do a bit of introduction, and then we'll move on to drone Cubesat connection, because I think I'll have to introduce what a Cubesat is. And then from Cubesat, you will understand what a Cansat is. And then I'll display what has been done in Nepal for Cansat, and then how PX4 has been implemented on it. All right. So my schooling was done in Nepal, Korea, and right now in Japan, involved in 4 different projects, including BIRDS 3, which is the one that I'm currently leading. And we also built the first satellite for Nepal called Nepalisat 1, alongside Ravana 1, which is also the first satellite for Sri Lanka. And the way I got into Cansats, the main reason why I'm doing this presentation is because of the leadership training that I received in Hokkaido University. And since then, I've managed to do 4 different, actually 6 different Cansat programs in Nepal. Okay, so let me move on to Cubesats. So what are Cubesats? So it's basically a satellite standard for nanosatellites. Nanosatellites are 1 to 10 kilo class. The size is anywhere, you can make it bigger, but the standard size, 1U size, is 10 by 10 by 10 centimeter, weighs about 1 kilo, and are single watt systems, right? So what you can do basically is stack them. So you can take a 1U and then make it 2U and make it 3U if you need more power or volume or size, okay? So these are not big systems. You can fit them in your hand, as you can see with the Rubik's Cube. If you look at the trend of Cubesat, it's growing exponentially every year, which is good news for us because we have more players. That means more innovation. Kyushu Institute of Technology ranks #1 in the world for small satellite launches from universities. Okay, so we have so far launched 16, and this year we're planning to launch 3 more. That's part of the BIRDS 4 satellite project. So we have excellent center for nanosatellite testing here at QTech, and as you you can see we have space environment and also we have rocket environment testing. So these are all the satellites we have tested in QTech, including Birds 3. This is basically a typical timeline for what a project, CubeSat project looks like. You can see that from kickoff to deployment, it takes around 1.5 years, and then we go into operation mode for 2 years. These are some of the images we have received from space. We have received images of Nepal, Sri Lanka, and Japan. These are the stakeholding countries. And we have collaborated with other countries to downlink their images as well using our satellites. It's also recognized worldwide. We have won the 2017 Diversity Award and also Better Satellite Award in 2019. So let's move on to drone and CubeSat connection. So what I feel and what I see, at least, and this is just my opinion, is that drones are fast followers of mobile technology. So whatever technology is being developed for mobile phones, it's slowly trickling down to consumer drones. And from there on, what I see is that CubeSats are basically following the trend that drones are making. So all of the technology that are being implemented on drones are slowly being trickled down to CubeSats. So basically, there is just two main aspects of it, right? So if you really talk about it, it's software and hardware. Let's look at operating systems for satellites. So what I've seen through my personal study is that the use of operating system is increasing year by year. So what I see is that in the future, we'll have more implementation of operating system. The most of those operating systems are free and open source. You can see that educational organizations and private companies are utilizing free and open source softwares. But the issue has been they are not reliable enough. Reliability is still an issue. For the highest mission success, you can see that the satellites with no operating systems are performing the best. And CubeSats are also dependent on the market. So we are using commercial off-the-shelf components, using processors and sensors that are available in the market. What we also see is that there is an increasing trend in using STM32, even in Japan, which primarily uses PIC for space systems. They're slowly changing into STM32s as well. This is very common that I saw in drone systems as well. So since there is a strong supply and strong demand for STM32s, I think this is going to be the standard in the future as well. So this is basically coming up from the drone industry, as you can see. So if you think about it, there is a lot of design similarities. You have constraints in power, weight, volume, cost. Attitude control is a little different because drone is airborne and satellites are spaceborne. But then you're using COTS, you're using the sensors, you're trying to do wireless communication, and reliability is always a factor in it. So I think everybody can sort of resonate with this. We go through the TTT standard, test, test, test. I think with drones, you do that as well. At least through a perspective of somebody who develops CubeSats, I see that drones have mature open source operating system, have mature software in loop simulations, are network connected, and use AI. So they are already doing edge AI. So there is already a talk of software-defined drones, which is very interesting. So if we were to follow the path, let's say we were to implement what drones used, then we can repurpose the operating system that drones have used, right? we can repurpose the software in loop simulations. And since we have access to drone hardware supply, I think the future can be protected that way. So we could, if we're following the path that was set by drones, then we can probably talk about software-defined satellites in the future. So let's talk about Cansat development in Nepal. So what are Cansats? Cansats are non-flight satellites primarily designed for educational purposes. And it's a tool to prepare students and faculty for future CubeSat projects. As you can see here, a can, you can fit a can as a satellite inside a can. And you can see that as it has evolved, there are components used from drones. There are also rovers that are sort of pseudo Cansat, pseudo rovers, and these are specially used for bring back missions in a competition called Alice. You'll notice here, Jay is here from PX4. So the way I got into CubeSats is also through Cansats. So Cansats are very important for anybody who's starting out with CubeSats. So I began with Korea Cansat competition in August 2014, then got to participate in Cansat leadership training program, which trains people to go back to their country and then start Cansat programs, right? So Nepal didn't have any Cansat program before. So I launched a pilot program in Kathmandu University in December of 2016. And then since then, we have done it every year. The one that I'll be focusing today is the one that we did in September of 2017 in Institute of Engineering. One thing to note is that all these programs are free. And also, as we move on to 2018, 2019, and 2020, we are trying to target a younger audience while using the next generation of trainees. So there's a new generation of trainees and a new generation of trainers, right? So that's the model that we are moving forward in. So let's look at PX4 being implemented on the Cansat. As you'll notice that these are just drone components. You have GPS, you have, so what I did was I just used the Wi-Fi for communication. And then you have the onboard computer, which is the PixRacer. This size was perfect for me. And then for EPS, I didn't use this board, but I used another board. But basically, the idea is to distribute the power and charge the LiPo. And then you have the battery, which is a standard LiPo that you can buy off the shelf. And the structure was designed in SolidWorks. The structure is then printed out using 3D printing. In mechanical engineering, we call it additive manufacturing. That's just a nice way of saying it. And then you have, as you can see from before, it's just been neatly packed into a small, let's say it does look like a pico satellite. So 50 by 50 centimeter and then 75 centimeter. And then you have a parachute here that goes and attaches here so that it doesn't fall straight to the ground. And this is just an example of the testing. Once the hardware is integrated, all I had to do was load the PX4 firmware and then link it up with Wi-Fi. And now I had a Cansat that was working. So I was using all the sensors and let's say the GPS and everything from drone and then utilizing on a Cansat. And what I did was I tested the distance because distance does matter in our case. And 100-meter transmission test between the Wi-Fi of the laptop and the Cansat was possible. And for on the laptop itself, for ground station, I use Q ground control. So just a standard way of using drones as well. So this is the these are some of the images that were taken during the 2017 CANSAT training. You will notice that students are using the PX Racer, and they're placing it on the structure, then loading up the firmware and then testing it. Yeah, so the next picture will show, next slide will show how we deployed it. We didn't have any deployment mechanism at the time. So what we did was we basically climbed to the top of the building, to the roof, and basically threw the CANSAT. And probably around 10 meters of height. So the 100-meter was that we tested was more than enough. After, let's say, deploying, we then did data analysis. The students looked at the data and then tried to analyze how the CANSAT was moving, how much distance it covered, and so forth. So if you look at the future, there are a couple of challenges. First thing is, it cost me $100 to make one of those CANSATs. And that's still high because an engineer's income in Nepal is $300. I think this is really funny, probably in Switzerland, but that's the reality back home. So that's a significant amount, right? $100. And another issue I saw was that components, let's say I want to buy Pix Racer in Nepal, it's not possible. So component availability is also an issue. So what I challenged the next generation of trainers to do was to build up CANSATs with components that are available in Nepal, right? So use what is available in Nepal. So that was what we did since 2018. That's why we had to discontinue using PX4. But then because of the pandemic, I'm starting to look back and see if I can leverage drone technology in CANSATs and Cubesats. So let's have a look at the future then. So one of the things that Jay from PX4 and I've been working on, basically he's been doing the work, is on the software in the loop simulation. So that's a game changer, I think. All you need is a laptop, and you can program and then run that program on to the simulation. In this case, it's Gazebo using PX4. And that allows us to adapt to social distancing as well. And there is potential for future virtual CANSAT trainings and competitions. And these are going to be very low cost because laptops, most people already have laptops. You don't need to invest in a separate CANSAT. And I think there's huge potential in this area. With that, I would like to just conclude my presentation. Thank you.
Avas, can you hear me?
Yeah, sure. I can hear you.
Awesome. Can you please let me see if we can see your your face again.
Should I stop sharing?
I'll do it for you. Don't worry.
Okay.
We got it.
All right.
That's why I'm in control here. I feel like an octopus with my million hands moving all the controls right now. Thank you for that. That was really cool.
Yeah, no problem.
All right, so let me just do one small thing. Really quick. All right, guys. Welcome back to the PX4 Developer Summit. Your host here, Ramon Roche. Please raise your hand in the chat if you thought that was really cool. Yes, the emojis work. Thank you, Avas, again. We're really inspired by the achievements of your project. Thanks for being part of the community, and we look forward to the next 7 PX4 satellites in space, right? Yeah. Yeah, definitely. Having satellites in space with PX4 is a game changer. All right. Thank you for your time. Talk to you soon.
Yeah, thanks.
All right. So let's see what we got here coming up next. So looks like we got next up Skynode Ready for Liftoff by Lawrence Emerly. He's the head of product marketing out there, and he's calling from Zurich with a very special announcement. So let's hear it from Laurent. Give me a minute while I connect you, right? All right, here we go. Ha, looks like that didn't work. That's why we're live, right? So we can handle those mistakes. Give me a moment while I really fix this out real fast. You know, you can prepare for weeks and weeks at a time, and still these issues will come up. Your internet connection will go down. You press the wrong button. You cancel the stream. It's fine. It's all good. We can get it done together. All right. Looks like I'm ready to go. Now, let's go back to Laurent. Thank you.
Hi, my name is Laurent. I'm head of product marketing here at Autharion, and I hope you have enjoyed the first part of the PX4 Dev Summit. I'm super excited to see how many tuned in to attend this year's event. 2 months ago, here in this room, our co-founder, Lawrence Meyer, announced the next big thing after Pixhawk. Many of you probably attended the webinar back then, but let's quickly recap. So why do we think Skynode is the next big thing after Pixhawk? It's for 3 main reasons. Number 1 is the combination of components that are integrated here in this compact module. It's first and foremost the flight controller, which is based on the next-gen FMU V5X. There is also a connectivity module built into Skynode, and there's a mission computer, an IMX AQM that runs the autonomy engine, the payload manager that enables video streaming, enables security with a secure bootloader, and that allows you to run your own code on board the drone, giving you complete freedom to operate. All of this is embedded in this compact design that comes with or without enclosure, and that fits even into small systems. The second reason why Skynode stands out is that it's not just the hardware that we're going to deliver to you, but also the pre-installed software, which is on one hand the complete flight control stack based on PX4. And on the other hand, it's our operating system that runs on the mission computer and enables all the functionality that I mentioned before. You can use MAV SDK to work in a known development environment and leverage the mission computer for your own advanced functionality on the drone. The third reason why Skynode is special is the connectivity. The fact that Skynode brings your drones online, allowing you real-time data transmission for telemetry or eventually data captured by your payloads. That means for your commercial end users of the drones that they can easily integrate this data into their own IT systems and own IT workflows using the connectivity. It also means that you can operate your drones from anywhere in the world over the internet, just like we demonstrated 2 months ago. Now what's next? As we announced, we're going to start taking orders in August. But at the same time, we're also going to start our early access program, which means that the initial batch of Skynodes is already going to be ready to be shipped by that time. And if you want to become part of that early access program, head over to our website using the link below and register today for the program. That's it from my side. Thanks for tuning in and enjoy the rest of the PX4 Dev Summit.
Wow, did I hear that right? Did he just say early access program? I think he did, right? So join Slack, make sure you ask Lauren how to get in there. Let us know in the chat if there's anything else we can do for you. The community volunteers are there to help you right now. Welcome back to the PX4 Developer Summit. Your host here again, Ramon. Thank you, Lauren. I'm sure there's a few excited community members right now out there. Community, please make sure you join us on Slack. Our awesome community volunteers are posting links on the chat room. Next up, we got What's Up With Your Battery by Hyun Lim, co-founder and CEO of Ubify. He's going to be calling in from Seoul, Korea. Give me a minute while we connect you to Korea, all right? All right, so let me just quickly try to set up my environment. I got Hyun on the line. He's getting ready. All right, so this is why the community is the best. What? Okay, guys. Right. Hyun, are you on the line? All right. Community. This is Hyun Lim calling in from Seoul, Korea. He's the co-founder, CEO of Ubify, and he will be talking to us about their new battery system. What's this all about, Hyun? Can you please let us know?
A battery. Basically, this is one of the most important thing in the drones. So to introduce myself briefly, I'm the CEO of Ubify, and my GitHub ID is Hyun Lim, and I wrote some survey paper regarding some open sources, and our company is doing drone light show with this smart battery. So drones love this energy bar a lot. So do we use this energy bar in the right way? That's the key question today. Our old friends, LiPo alarm, you may use to it to prevent undervoltage problem. And LiPo balancer is solving the cell balancing problem. But do we really need this equipment? With smart battery, probably not. So the first electrical vehicle, and between the modern electrical vehicle, the main innovation, I think that is a BMS, battery management system. So everyone was on the same line in 2014. Even this famous consumer drone was using a battery without battery management system. Now all has been changed. What's been developed since 2014 and why? The first job of the smart battery is protection. So the protection is about knowing when it is danger, the short circuit, hot temperature warning. That's the main job of the protection. And prediction is know when it will be empty. That's very important. So the gauge indicator indicates the very state of charge in percentage. And precaution is know when to stop use. For example, as long as you are using the battery in 100 times, 200 times, it degrades. So it's important to know when we have to stop the use of the battery. So cycle counter and remaining state of the charge is in charge of this. Even smartphone implemented this feature, a smart battery, in just in 2019. Why? So this is a user interface of iPhone, and you can check the maximum capacity of the battery, which is basically a state of health, which indicates the when you should change the battery. Because it is complex electrochemical device. Even though it looks simple bar, that's pretty hard. So, but the most important question to this energy bar is, how do we know how much percentage of energy left? So you might use to this gauge and even this small patches in a consumer battery shows the desire of knowing percentage of energy left. So just by looking, you will see the same battery, but it has different level of energy. How do we know inside a battery? So basically, it's very hard to know, because the one metaphor you can imagine is a gas tank of the car. How does your fuel gauge of the car know the level of fuel? Can you guess how much fuel inside this fuel tank? To figure out the fuel gauge, there are a lot of devices involved. Even this measuring simple oil level is complex. So measuring the battery is also very complex. So how can this achieved in the PX4? In the PX4, based on voltage and current measurement, there are simple estimator inside. So this estimator estimates the remaining capacity based on internal resistance of the battery given by a user, and also the battery voltage and the current consumption. However, this is not working 100% always. For example, someone get 100% level still, even the accumulated consumption is this much. Why is it not accurate? That's let me answer to this question in a few ways. First, you can imagine a battery in this diagram. So even though the battery model itself is a simple, there is a self-discharge resistance, a series of resistance. Those unknown variables are main factor of battery uncertainty. And even this uncertainty is depending on the temperature, time, and remaining energy. So even the battery is complex. Let's start with the simplest model, modeled by a resistor and capacitor. So the battery experiencing IR drop, which is drop of voltage because of the current flowing into the internal resistance. So V loaded is the dropped voltage that you will actually measure. And the graph is moved down if the resistance increases. In case of you are using more than 100 cycles, you will experience resistance increases, and also the load current increases, and also the temperature decreases. So by just by measuring this fully loaded voltage does not give you a proper level of energy. So what this makes confused, so usable capacity versus original capacity. So all the label of the battery shows the design capacity, but you are not able to use that energy 100% because of internal resistance. So some of the energy is consumed by battery itself. So you will have slightly under voltage than open circuit voltage, which is a true level of energy based on the open circuit voltage. So you will end up with the actual maximum is less than the chemical maximum based on how you consume the battery. So the resistance curve change over temperature. So this is a graph of the resistance curve based on the temperature. From 0 to 50 degrees Celsius, you will see a pretty large gap between the temperature. So the impedance, which is internal resistance, is strongly dependent on temperature, and also by using the battery more than 100 cycles, you will experience also the change of resistance because of age. So this shows the battery aging. So in a cycle 1, it will show most top graph here, while the cycle 100 shows a slightly less voltage, and also internal resistance changes like 2 times. So this resistance change has to be addressed to measure the proper energy level of the battery. Also, the transient response makes us hard to estimate a battery level. For example, the voltage when the load is on and off, their behavior is different. So when it is on, it has this curve, and when it is off, it has this curve. The most difficult thing is to recover from the load removal to the original open circuit voltage. It takes about 2,000 seconds. So right after the load removal and 3,000 seconds, the voltage difference is somewhat over 20 millivolts, which is quite large. So this also difficult factor of estimating a battery remaining. So like EKF, we need an estimator of battery capacity. Still, how do we know how much percentage of energy left in the battery? So how to estimate a battery capacity? There are one well-established model to measure change in capacity, voltage lookup, and Coulomb counting. This is done in the PX4 too. And the other way that has developed is to develop a cell model, which is modeling a battery in a proper mathematical model and calibrate the model parameter in a proper environment that will give you a better accuracy of battery estimation. So the voltage lookup, you can imagine this. In a glass of water, to measure the amount of water inside the cup, the most easiest way is reading a water level by looking. However, to have a confidence in that level, the water has to be stationary. Likewise, to read the voltage to figure out the remaining capacity, the voltage has to be stabilized, which means at least 2,000 second waiting, which is almost an hour, and also the temperature is important. So this ideal situation is never given in when we operate the drone. Also, the open circuit voltage curve is important. For example, the capacitor, also the energy storage, it has open circuit curve like linear here. However, the battery could be regarded like the cocktail cup. So initially it increases voltage very fast, and it has some flat curve here, and then at the last it also increases in a steep. So this is a hard part of reading the open circuit voltage of the battery. So it is not linear. As it is not linear, if you not model this steep curve, will fail to estimate a battery level. Also, the other way is a current integration. So this is somewhat called a power brick in the PX4 Pixhawk. One can also measure how much current goes in and out in a system. In battery, capacity changes can be monitored by tracking amount of electrical charges going in and out. Simply just adding up how much current flowing or draining into the system. But how do you know the amount of charge Q0 already in the battery at the start? For example, when we plug the battery to the to current power brick in the PX4, you will have 100% at the beginning, but that's actually not true. So how do you count charges accurately? Also the problem, because shunt resistor also have uncertainty over temperature. So our main concern is how much capacity is really available. So to figure out this, we have to figure out this internal resistance in an accurate level. But the problem is internal resistance is different over remaining energy and also the temperature. So what we are really looking for is available capacity here. So the design capacity is basically a label on the battery. So it shows some numbers like 3,800 milliamps. Such number is a design capacity. The full charge capacity is actual amount of energy inside a battery. Sometimes it's over the design capacity, and sometimes it is under the capacity. And what we really interest here is available capacity. How is this known? So you may experience some very uncertain level in the iPhone, for example. Even though it has like 20%, it just suddenly drops to the 1% and goes off. So even this like billion selling consumer level device is failed to estimate this available capacity. So this is also hard in the drone battery too. So there are a few different fuel gauging methods available. First is a cell voltage measurement, which is implemented in the PX4 too. It measures the cell voltage. The advantage is simple. Just by measuring the cell voltage, it shows some idea of remaining energy. However, as I talked about it before, there are many variables that makes this voltage measurement uncertain. So it's not accurate over load conditions. It's accurate when you stay the battery about an hour and measure the voltage. The other way is a Coulomb counting, which is counting actual energy put in and out to the system. It measures and integrates the current over time. However, it is affected by cell impedance, affected by self-discharge too. So to mitigate these issues, there are impedance track algorithm has been proposed by Texas Instruments. So it directly measures the effects of discharge rate, temperature, and age and other factors by learning cell impedance. So cell impedance is the most critical factor of estimating battery capacity. So what is impedance track does? Impedance track keeps the table in a data flash first. So open circuit voltage is kind of very important characteristics of the battery. Regardless of capacity, if a group of battery is using the same electrode, they will have the same open circuit voltage trends. So if we do know the depth of discharge, function of depth of discharge to open circuit voltage, we can estimate the energy level. Vice versa, the depth of discharge can be estimated by open circuit voltage. The depth of discharge means the remaining capacity, for example. And as we know, this is resistance here is internal resistance. So it calls the voltage drop over open circuit voltage according to the load. So impedance learning is possible when we know the open circuit voltage. This is actually predictive variable or function of this. And actual measurement of voltage and current will give the impedance value here. So the impedance track represents the tracking of this impedance over time by measuring voltage and current accurately while we have a model of open circuit voltage of a certain battery model. So here also Qmax is updated based on every iteration. So this will help the accurate estimation of the battery. Also, the run periodic simulation of remaining and full capacity by predicting open circuit voltage based on depth of discharge. And this is a function of also the internal resistance. So to measure the resistance, data flash is a data table inside this SoC, contains a fixed table of the function of temperature in SoC, which is output is open circuit voltage. So impedance track algorithm doing real-time measurement and calculation during charge and discharge. So it basically calculates the voltage drop accurately so that the algorithm testing the current table and determine whether that table will be updated or not based on the differences. And also because of the curve, the discharge curve of the battery, as you see, the beginning is very steep and there are some flat region going through, and you will end up with very steep drop of the voltage. So to aid these characteristics, impedance track algorithm checks the impedance every 10% of depth of discharge until the 80%. And then from 80% to until the fully discharged, it has a 3% intervals. So it has a more fine level of the resistance measurement here. So by iterating this, as battery current is consumed, it will update the resistance value like this. So every iteration from depth of discharge 0 means the fully charged, and this is a fully discharged. It updates the table of the resistance. So every single region, the resistance value is changed. So here is the most critical part to estimate the remaining capacity. What is the benefit of this fuel gauging and impedance track? For example, this is one example of if you perform the voltage only shutdown, you will end up with 120 minutes runtime in this given condition. However, if we drain the battery until the 0% based on impedance track algorithm, you will end up with 168 minutes runtime. So basically, you can extract the all energy from the battery based on the accurate information. So the typical smart battery architecture is like this. So here, a discharge and charge MOSFET. So enabling this MOSFET will enable you only charge or only discharge or both enabled. So if you have some undervoltage problem, then the charge MOSFET is open so that no current could be consumed. And also, discharge. And also, when there is an overvoltage problem when doing the charging, this charge MOSFET is closed or open to control the current flow. And this is called the gauge integration circuit. So the gauge integration circuits from beginning to the end of the disposal, it calculates the internal resistance and current consumption all the times, and it outputs the information through the AirSim bus, which is standard of this battery system. And there is a chemical fuse. If there is some critical problem happen, then it just blows up the chemical fuse. So these are typical smart battery architecture, and for now the AirSim bus is implemented in the PX4. Also, the UAV CAN is implementing. So you can check out the drivers and AirSim bus. This is a basic implementation of battery AirSim bus on the PX4, and also we developed the PX4 compatible smart battery, which means in AirSim bus, and the battery spec is 4800 4S AirSim bus, and fully calibrated and tested 90 amp discharge is possible. The nice thing about this smart battery is because it controls the charge and discharge FET, you can just use a simple charger like this. The current is controlled on this charger. The only function required of the charger is controlling the current, so that it should no more than 1 C of a battery capacity. So here is a voltage graph when we use a smart battery. For example, it starts from the 16.8 volt, which is the typical max voltage of the 4S cell, and it sharply drops until 16 volt in 1 minute. And then there is some flat region that's going on, and there is some as it is drained, the curve becomes steep like this. However, measuring and estimating the battery capacity from this voltage graph is somewhat uncertain in this region and that region, because it is not linear. If you draw some straight line from here to here, it's pretty not matched. However, the state of the charge graph is linear, so the impedance track algorithm calculates the state of charge accurately from 100% until the 5%. So it calculates the state of charge linearly, so that we can linearize the response of the voltage into the state of charge, which is a percentage-based, more informative. So here is the end of presentation, and what I presented here was the battery characteristics and what's the advantage of smart battery. So I'm happy to accept the question. Thank you very much.
Can you hear me?
I can hear you.
Awesome. Thank you for that. Can you stop sharing your screen for a moment? Let's see if we can change your video view.
Sorry?
Just wanted to know if we can change your video instead of your screen share.
Okay. I stopped.
Yeah, No worries. Thank you. I just wanted to thank you. That was really interesting. There's a few questions on chat. Unfortunately, we're running behind schedule. So why don't we do this? Why don't we jump on to the PX4 Slack?
Okay.
There's a PX4 Dev Summit channel. Let's jump on there. Let's try to answer questions from the community. And I'll get back to you on that.
Thank you.
Sounds good. All right. Thank you, Hyam.
Thank you very much.
All right. So let me just end my call here with Hyam. What do we got up next? Oh, nice. Look at this. Hey guys, welcome back to the PX4 Developer Summit. Your host Ramon Rocha here. I'm still here in Tijuana. I'm still streaming to you. We're still live. I can't believe my laptop has survived this far, streaming without nonstop interruptions. This is amazing. Thank you everyone for the response. This is exciting. Like seeing all those live views right now, it's making this really worth our while. Gotta be honest, like we were planning for this event, and just like last year, we didn't really think we were gonna get so many registrations. It's crazy. Thank you. It just means that this community keeps on growing and that this industry is going really big. Next up, we got a really interesting conversation with Tuli Food. Do you guys know who this guy is? I'm gonna give you a quick look at this. I just got this dropped by the mail this week. So next up we got What's the Difference Between a Drone and a Flying Robot by Tuli Food. He's joining us from San Francisco, California. He's the Community and Business Development Manager for Open Robotics. I'm really excited to have him here. He's also a repeat speaker from last year. Make sure you guys are joining us on Slack. Community volunteers, please do me a favor. Post the link for Slack again. Let me just connect you to Tuli and I'll be right back. And hopefully that standby video audio gets fixed by now. Let's figure it out. All right, we're back, guys. Welcome back to the PX4 Developer Summit. Welcome to the next session. What's the difference between a drone and a flying robot by Tuli Food, Community and Business Development Manager for Open Robotics. I'm really excited for this one. I gotta say that I'm a big fan of Tuli. Sorry, I'm a fan. He's been doing awesome work on the ROS side, and the ROS community. I want to say something quickly about the ROS community. Let me just go back to my live webcam. Hey, hi, if you're joining here from the ROS community, welcome. We want you here. We want to interact with you. Please let us know if there's anything we can do to make your life easier as a ROS developer. There's nothing better to us than having other fellow community members join our community, try to set up our stuff, run our tutorials, let us know if there's anything that's not sure, that's not clear. We're always on Slack trying to help you out. We're really doing a lot of effort to make sure that ROS compatibility is up to date and working really good out of the box. So having said that, welcome everyone from the ROS community. I'm gonna get the mic back to Tuli. Tuli, you're still here? All right, so moving back to Tuli. Hi, Tuli. How are you? Thanks for joining us. I'm going to leave you the mic all for you. Go ahead. Hey. Mic check. Let's do this. Let's go back to the standby screen and let me check your mic levels real quick. Community, sorry, live stream. Give us 1 minute. We'll be right back and we'll make sure that Tuli is back with you in a second. Hello, community. Can you guys hear us? It's only my mic for now. Just want to make sure my mic is good. Like I said, I was saying earlier, like there's so many things we're dealing with right now. Hear ya. Great. They can hear me. All right, so let's do this. Let's really quickly go back to you. Hi. Can you guys hear Tuli? We need confirmation. Confirmation from community volunteers right now? Not yet. That's incredibly frustrating, especially when it's the same setup as the last speaker. Check again. You know, Tuli, let me go back to this and I'll be right back with you.
Sorry about all the delays, folks.
Yeah. Hi, we're back. So, Tuli broke the internet. I'm sorry. What did you do?
We don't have enough bandwidth here in Silicon Valley.
I think something's broken between BVLOS and PX4 compatibility here.
Sounds like people listen. People sound like look like they can hear us.
I think they can. All right. I guess we fixed our audio issues here, guys. Thank you again for sticking with us live stream, right? Thank you, Tuli, for sticking with us. Of course. Now go back to you. I'm gonna mute my mic now. Thank you.
Thank you. My pleasure. So, as Ramon mentioned, I'm Tully Foote from Open Robotics. My role is the Community and Business Development Manager here. I've been doing robotics for my whole career, but flying has had a special place in my heart all along. My grandfather was a pilot and loved building model airplanes. He flew a lot of passive gliders and was an early adopter of remote control back when it was highly advanced to have a single servo, and it was just pure analog control from a joystick in your hand. I caught the bug, blazed my own path, becoming a helicopter pilot instead. I've built a hovercraft, I've flown drones, had a lot of fun. So, I have the title, What's the Difference Between a Drone and a Flying Robot? I wanted to use this to inspire thoughts and discussions within the community and thinking about how to connect outside of this community and etc. As Lorenz mentioned, ROS has been a component of the PX4 ecosystem for a long time. We've been collaborating on projects from the early days back at ETH Zurich. And there are a lot of tools in ROS that you can leverage in this community. I'm going to highlight some of those, but I also want to take this opportunity to challenge the community to think even bigger. ROS is but one large project out there with lots of resources, but there are many more. And a lot of this comes from our mission at Open Robotics, which is to facilitate open source robotics, which includes drones. And there's also a much, much larger community out there of projects, etc., that we can all leverage. Just a bit of background on Open Robotics ourselves. We have a team spread around the world working on all sorts of projects, cars, drones, etc. Lots of fun stuff. Specifically, we have two main projects that we work on here at Open Robotics, the ROS project, the Robot Operating System, and Ignition Gazebo now. These are two large projects. They arch into many, many types of robots, have a huge community around the world. But we're happy to be pushing forward to getting these into the next generation. Many of you are familiar with Gazebo and ROS. They've been going, both of them have been going for well over a decade. And we are pushing into Ignition Gazebo, which is the next generation of Gazebo. And ROS 2 is out and ready to go. Speaking of which, we have just released ROS 2 Foxy Fitzroy. This is our second LTS release of ROS 2. And this is the one where we really think that it's time for people to pick up the torch and start carrying ROS 2 as the primary mantle to think about what you're doing for ROS versus ROS 2. We're ready to say it's time to switch forward. And ROS 2 is being driven by Open Robotics, but we are actually now a small component of the ecosystem. You can see here the logos of our TSC. Oh, wait, I should be presenting, shouldn't I? Sorry. Now you can see the logos of the TSC. These are lots of companies from all around the world using ROS 2 in many different environments. And we're happy to have them all coming on board now. So to give you a sense of scale of what's happening in the ROS community, we have well over 300 companies, many of them big, some of them small, many small as well. I looked at the numbers for last year and we had over 260 million binary downloads of our Debian packages. We have 35,000 users on our Q&A forums, 5,000 users on our discourse instance. We have over 2,000 repositories indexed, and we've got hundreds of thousands monthly visits on our websites. And if you're doing research, there's also over 7,000 citations of our first paper from 2009. It's a great community. I encourage you all to get out and explore it. I'll give you some highlights here, but I'm really just going to be able to gloss the surface in this quick presentation. So now, onto my main topic. If you take a look at this picture, I'm going to say, how many of you can see a duck facing to the left? And how many of you see a rabbit facing to the right? Good news is, in my survey of everyone that I saw raise their hands, it's a tie. And you can see it either way. So really, this is a matter of perspective. And some people see it one way, some people see it the other way. And depending on where you're coming from, what your perspective is, you can see it from either way. A lot of the PX4 community is coming from a microcontroller side. A lot of general robotics is coming from a large microprocessor side. And when you look at the problems, they're the same problem, but you attack them in different ways, etc. And the goal of this talk is to have you become aware of your perspective. And your perspective is not wrong, but sometimes it's valuable to be able to think about what the other side is. So if you can't be aware of how the other side sees things and approaches things, you're basically going through your project and might be basically thinking about it with blinders on, and there's other valuable approaches. So when you're thinking about these projects and when you're approaching something, you want to be able to think about what are your unique constraints, what are you sharing, what can you share, and what can you leverage from the rest of the community. There's the ROS community to leverage, there's greater open source computer systems, and other projects that have lots of great things to take advantage of. And this talk, I'm going to be focused on practical open source. There's a lot of talks about philosophy of open source. And I'd love to talk more about that, but with limited time, I think that because this is an open source community already, I'm going to skip that and leave that as an exercise to the reader already. So there are many ethos of global open source communities. With ROS, we've really worked on making sure that we can have federation, simple, small composer utilities following the Linux model, and we don't want to reinvent the wheel. There's a lot of content that we are out there, and if we can leverage pre-existing things, we don't have to rewrite it. So we're looking for ways to improve our efficiency and reduce our effort to be able to get the same results. If 2 of us work together, we can do twice as much work. If there's 100 of us, we can get 100 times farther. And there may be some overlap and inefficiencies in how much we can share, so we may not get 100 times more work. But if we can only get 50% overlap or improvement, that means that we'll still be 50 times more efficient. So if everyone shares a little bit, the network gets bigger and everyone benefits. So specifically, I want to call out reuse. And this is when you can take advantage of what other people have done. And on the other side, there's sharing, which is the flip side, because if you can take advantage of the work I've done, I need to share it back to you. And obviously, these are great things to do. They're not all perfectly positive. There are costs that you need to be able to verify the stuff that you're going to reuse. If I share something with you and it's not up to the quality standards that you want, it can be a lot of work for you to test and improve it to make sure it meets your standards. And so we want to be clear about our communication and make sure we're sharing those things in ways that can be leveraged effectively. And similarly, there's extra cost to sharing. I want to go through a little bit more polish to make sure to communicate to you that it works as well as you would expect it to work. And it's not always true that you should share everything. There are things that are unique to certain situations. And if this thing is useful only to me, the effort to share it may not be right to do. May not make sense because I'm going to spend extra effort to share it. And then it's not useful to you because it's unique to me. But the important thing is when you're looking at these things is make sure to remember to avoid the not invented here syndrome where you don't think about something because you didn't think about it. So we're a little tight on time. I'm going to speed things up and blitz through the rest of this. But there are a lot of things in the latest ROS 2 release, and I'm just going to highlight a handful of them here and remind you again, don't think about the challenge of not invented here. There are many things out there. They're done well. Find them and take advantage of them. Looking at ROS 2, one of the things that I think would be super valuable to drones is that they get larger and become systems of systems. We got to start thinking more about multiple process launching. There are tools out there for that. Don't reinvent those. Topics, communication. There are a lot of things out there, standard messages that can be leveraged and are already used by a large community. Don't reinvent these things. And if you're interested, I'm also still working on Rep 147, a standards interface for aerial vehicles. Love to get more buy-in and input on that from this community. And in addition, when you're doing this communication, there are lots of things like quality of service to help you with urgency and reliability over limited bandwidth link, as well as authentication, encryption, and access control. There are tools out there. Don't reinvent them. If you need to visualize 3D data, arbitrary data, you may not know what's in your payload. You want to be able to be expandable and add new data types or new sensors quickly. There are tools for that. Bag files are really valuable. They let you collect arbitrary data, keep it in a self-documenting way, play them back. It can be used for machine learning and training, unit tests, facilitating collaboration with people that cannot fly with you, and also relatively easily used for black box recordings where you can keep track of everything that goes on. there are lots of things as we start to scale up to more vehicles, more base stations, asynchronous and synchronous remote request procedures. There are lots of tools for that as well. This was mentioned in some of the earlier talks. We have tools for keeping track of transforms and environments. One of the things I'd love to see a little bit more is parameterized templates for drone descriptions so that we can simplify the launching process and coordination of standardized drone platforms. There's a ton of moving and planning infrastructure out there and projects doing these things. I'd love to see more integration with the PX4 community in these areas. In particular, I want to call out Move It. And SLAM and navigation. There's a whole lot of research in this area. Drones are somewhat different and somewhat unique, but don't discount everything else that's already happened. And of course, simulation. There's a lot of it out there. I'm happy to say this is something that's already been moderately well integrated into the PX4 community. To highlight this, one of the things that I talked about last year, I put out a call for input on what people would like to see in a drone playground. And I'm happy to say that we have now landed the results of that in the PX4's main CITL branch. And if I press play, you can see the results of this. This is our best realistic simulation of the Baylands Park here in Sunnyvale, California. The trees are as close to accurate as possible. You can run into them. There are playgrounds, swing sets, these statues, everything is accurately texture mapped. The trees are as close as possible to the real world. If you are using Qt ground control, you'll see the exact same thing from it's realistic overhead data with the ground. So, and lastly, just to drop a mention of this, there's MicroROS, which is coming along, and looking at the microcontroller. I'm not going to say more about this, but look forward to Nuno and Jaime's presentation coming up later in this conference. So, one final thought for me on things in the ROS community that might be valuable to be able to be leveraged is that there's a lot of tools for packaging. This is something that the ROS community spent a lot of time on, as well as the greater Linux and open source communities. There's a lot of tools out there, and I think that considering leveraging these things would be great to facilitate more collaboration with the community. So to finish this up, I'd like to put a challenge back to you. I've listed a lot of things in the ROS community that I think would be valuable for you. And I'd like you as the PX4 community to think about what are some of the things in your community that might be valuable to the greater robotics community that you could share and increase the number of people with which you're collaborating. As I talked about, we want to get to bigger communities, bigger systems. And so if we can have this collaboration go both ways, that would be great. Just off the top of my head, there are great top-down mapping interfaces in the drone community, as well as free space planners and potentially situational awareness tools and fleet management things that might be valuable for, say, boats or cars. So think about what you're working on. Has someone else done something similar? Can you take advantage of what they're doing? And if you're doing something you think someone else might be doing similar, can you share what you're doing to let them take advantage of it? And as a last reminder, don't fall into the not invented here trap. It can be something, it'll decrease productivity overall, and it can be counterproductive to forward progress. We can all do more if we work together. So thank you, everyone. And a couple of questions I see coming in. So the Baylands Gazebo World is asked where you can get it. It's available in the default CITL launches now, I believe. We also are hosting it in the Gazebo fuel repositories. So if you go the standard Gazebo tools, you should be able to download it from there as well. It's a standard built-in library with all the models are available in our online repository. So another question is, compared to ROS 1, how lightweight can ROS 2 be? I don't have a good metric answer to be able to give you this, but we are really targeting to be able to run down onto microcontrollers. There's more information from Nuno and Jaime that'll be coming up in a later talk. But we can get down to a much lighter interface. And third question, what is the fundamental need for ROS, and why not just integrate ROS capabilities into PX4? So, what is the fundamental need for ROS? The underlying thing that ROS is doing is mostly facilitating collaboration by providing standard interfaces for people to talk between, as well as providing standard modules that people can interact, plug and play and swap out and do the collaboration. So if I write a SLAM module and you write a SLAM module, we're using the same interface and the same different implementation. We can plug our different implementations into the system moderately easily using ROS packages and ROS launch files and the standard ROS interface. Why not just integrate ROS capabilities into PX4? That's a great idea. I think that we are making good progress on going in that direction, being able to make the bridge between ROS and PX4 much smaller. And again, I'll refer you to Jaime and Nuno's talk coming up in a little bit. So, thank you.
All right, thank you, Tully. Hey, guess what? The community just awarded you with the best bird of the summit. Good job. They put you against me, and I lost. Thanks for your help. That was really interesting. Let me just switch back to my screen. Okay, thank you, Tully. All right, hey guys, welcome back to the PX4 Developer Summit. Glad our audio issues are gone. Thanks for your patience, everyone. I'm glad we're here with friends, though. It would be really hard if this was like a live conference or something. Looks like my camera is heating up. Are you guys seeing those blue screen of that? Looks like I need to reset something. All right, so let's do this. I'm going to introduce the new speaker while I figure out my issues here. Next up, we got Microsoft AirSim, Applications to Research and Industry by Ratnesh Madan. He's a senior research engineer from Microsoft, and he's going to be calling in from Seattle, Washington. We're really being all over the world today. Give me a minute while I connect you to Ratnesh. All right, community. Guess we figured out our audio issues server. I'm glad we're still here together. It's been an incredible morning for me. I'm in Pacific Daylight. And looking at all the community members that are across the globe, it just makes us feel so proud right now. Thank you for being here. Let's go with our next speaker, though. I have Ratnesh Madan on the line. Our next speaker is Ratnesh Madan. He's a research software development engineer at Microsoft. His session is titled Microsoft AirSim, Applications to Research and Industry. Before Microsoft, Ratnesh was a master's in robotics student at Carnegie Mellon University, working on perception and motion planning algorithms for quad rotors on the Air Lab at the Robotics Institute. He focuses on thing obstacle detection and mapping for UAVs and marrying traditional sampling-based motion planning algorithms with machine learning. All right, Ratnesh, you ready? All right, all yours. Take it away. Thank you. Looked like we have issues right here with Ratnesh again. It is audio issue, yeah. I'll figure it out in a second. After the last speaker, yeah, that gave me a heartache right now. Okay, so we are checking volume levels right now. Let me get the standby speaker queued up. My mic is still open, guys. I know. I'm testing. Thanks for letting me know. Let me just check audio levels real quick. Hey guys, sorry, audio issues again. I'm back with Ratnesh. Can you do a quick mic check, Ratnesh?
Hey, I'm Ratnesh. Can you hear me?
I think we can.
Can you hear you? Can you hear me?
Yep, that works. Good job. Yeah, after this, I guess I can do live streams for a living. All right, Ratnesh, it's back to you.
Okay. Thanks, Simon, for the introduction. Hi, everyone. I'm Ratnesh. I'm a research engineer at Microsoft, and I'll be talking about Microsoft AirSim, our open source simulators for drone, cars, and computer vision, and its applications to research and industry. Thanks for the PX4 Developer and Dronecode community for hosting me, and thanks everyone for joining from your homes around the world. So yeah, AirSim came out in the spring of 2017. And recently, we actually hit like a cool milestone of 10,000 stars on GitHub. As I said, it's a robotics simulator, and it comes with 3 modes: one for drones, cars, and computer vision in general, with a bunch of sensors, RGBD, semantic segmentation cameras, LiDAR, and a lot of physics-based sensors, so to speak, like barometer, magnetometer, IMU, and GPS. And it has been used extensively in research and as well as industry till now. So just to give like a quick architectural overview of our simulator, I think like most of the people attending the session would be already aware that the simulator's job is to take in control inputs and give back to you the sensor data. So in this right box, we can see like the actuator signals in AirSim. They can come from various sources. They can come from a C++ or a Python API and get routed through a flight controller in HITL or SITL. Or they can also even come from a manual, like an RC transmitter. And then these actuator signals go through, let's say, an actuator model along with some filtering, and then which basically gives us generated thrust and torque at the range point. And then there's also environment simulation, so you can have like local environment conditions at that actuator, like the air density or the gravity, and using all that you can calculate like the net external forces and torques acting on the vehicle body along with drag, and then basically all that is routed to a custom physics engine, which is going to compute the next force or the material, basically kinematics of the body. Now that kinematics can be applied to a bunch of sensor models, which will, and that's how IMU, GPS, barometer, magnetometer kind of things are implemented. And that sensor data can be accessible on the client side through the API layer, or it can be fed back through the flight controller. And basically, where the rendering engine comes is that like the physics engine, the pose predicted by the physics engine, it's gonna be passed. We use that pose to move the drone mesh or the drone mesh in Unreal Engine or Unity, and after that we can get like the camera data or the lidar data. And from the API layer, you can basically do your higher level autonomy or reinforcement learning, imitation learning based research, whatever you're interested in. So depending on like what your use case is, I'm just gonna highlight like a couple of use cases here. So on top left, you can see like a custom environment we built for the RAPA Subterranean Challenge. And the winning team actually generated synthetic data using that environment from CMU and OSU. And on top right, you can see a customized wind turbine model in which you can sort of change the speed at which the blades are rotating, as well as the deformation of the mesh. And then on the bottom, I'm just showing how AirSim can be used to essentially simulate like an inspection task pair. Here I'm using the ROS wrapper with a stereo pair. And along with that, I'm basically using Vox blocks, open source mapping library by ETH Zurich, along with some custom path planning and trajectory following. And here in RViz, you can basically see like the RGBD point cloud along with the reconstructed occupancy grid map. And now and then you can also see like the sign distance tree. So without further ado, I'm gonna go to the first research project I want to highlight. So this was a collaboration between ETH Zurich, University of Zurich, Microsoft, and Stanford, and we essentially organized a drone racing competition in Europe this year. So the drone racing is a very cool task, which brings, I think, like all the hard problems in autonomy together. So you have to do state estimation, map the drones, map the gates, and avoid the other incoming obstacles, which are essentially like the other competitor drones, and essentially plan a trajectory and follow it optimally in this complicated race tracks. And humans, as we can see on the video on the right side, are able to do this using just like an analog signal from an FPV image from a camera mounted on the drone. And then the inputs are basically body rate and thrust commands. And then, as is the case with a lot of games and tasks which humans are good at these days, there is definitely a research push to figure out how far we can go with autonomy to do a task like this. So depending on what kind of background you're coming from, you can formulate this in a very classical way in which you will do mapping, path planning, trajectory tracking, control, and finally figure out the control commands and send them to the flight controller. And of course, there are multiple modules in this case. So you will essentially start with something like state estimation, like visual inertial odometry, use that state estimate and computer vision to figure out what the trajectory you want to plan through. Or else you can go completely end to end. That's another extreme. You can take like the raw RGB image and basically train a visual model policy, an end-to-end black box, which will spit out the body rate thrust commands. Or you can, I think there's another push right now in which like people are sort of combining the best of the both worlds. So you can learn representations or come up with like traditional policy classes, for example, an RL or imitation algorithm, in which you will try to combine both the classical intuitions and the deep learning based way of thinking. So that's kind of like the motivation as to why we organize this competition, because we think like AirSim can be a great way to get people to work on this and make rapid progress. And in this competition, we are basically focusing on the top left red box here, planning and computer vision, and state estimation and flight control is sort of assumed to be done for you because it's a simulator. So the objective here is basically you have to fly through all the gates in minimum possible time without hitting an opponent drone. And I'll explain what I mean by the opponent drone here. So we broke planning and perception into 3 tiers in this competition. So in the first tier, which is planning only, you sort of know the ground truth geometry of the environment. You know where the gate poses are. You know the dimensions of the gates. You know where you are and also how you're moved. So you know your own state estimate, and you know the state estimate of the opponent drone as well. And then the second task is sort of a time trial format. In this tier, there is no opponent drone, but the gate noises which are returned from our API, they are corrupted. So you can see like they are still like roughly close to the center of the gate. So if like the next gate is not visible, you can still sort of use that noisy pose estimate to roughly steer towards its direction. But at the end of the day, you will have to detect it, basically figure out how far it's away from you and plan something and fly through it. And then tier 3 is essentially a combination of both the 2 tiers. So there is noisy gate poses, there's an opponent, and then I'm just showing like a couple of race environments from our track, from our competition tiers, and just to give a feel of what it looks like. Some logistics. We ran this competition initially in 3 phases. So the first phase was a training phase, which ran for about 9 weeks. And we saw quite a lot of enthusiasm across the world from people ranging from mostly academia and also some industry labs and startups, which was followed by a qualification round, which ran for 5 weeks. And then we finally filtered some teams which competed in the final round. And the training round, you were allowed to modify the racetracks however you want. You can sort of set the gate poses and sizes, but that wasn't allowed in the last 2 rounds. And just to highlight the challenges again, like the first challenge of this problem is certainly trajectory planning and control. And like the very cool thing about this was that, I mean, intuitively, you don't necessarily have to fly through the center of the gate. You can basically pick a point at the gate cross section and come up with an optimal plan. But there was essentially only one team who did that, and they won the first year. Secondly, there is dynamic obstacles of, obstacle avoidance of dynamic obstacles, which is like the other drone here. So this other drone 2 was basically sampling a waypoint in the gate cross section randomly and fitting a minimum trajectory and flying through it. There's cupboard abstraction and planning. So like you want to move in a way so that you hopefully maximize the amount of gates you will see after you pass this one. And then you would want to generalize to arbitrary racetracks. We didn't have arbitrary textures in the competition, but like different shapes, sizes, lighting conditions, different environments. So there were like 3-4 environments over which the racetracks were set. And also, of course, there are like always variable number of gates visible in the 3D image. And depending on what level of APIs, AirSim APIs you're using, you can have a lot of parameters you can tune. So you can go as high as to like trajectory planning and ignore planning and control completely if you want to focus on perception, or you can go lower down the stack up to attitude control for the competition, but in the future, or motor control as well. So this is just sort of highlighting the heat map of the register teams across the world. There were roughly 115 teams which registered. Out of them, I guess like roughly 12-13% of them submitted. We got 12-13% unique submissions in the qualification round. And after some filtering, we finally had 10 unique submissions in the final round. I've listed the winners in the matrix in the bottom here. And it was really amazing to see like each of the winning teams were like spread across different countries, and they were really enthusiastic and came up with novel approaches. So post the competition, we have been essentially working on improving our framework, and we are calling this AirSim Drone Racing Lab. Basically, a suite of extensions to the original AirSim simulator, and focus on the domain of drone racing. So they are like Unreal Engine level APIs, which essentially let you modify environment objects. And then they are like race APIs, which essentially help you orchestrate drone races. And then finally, there are like a bunch of control APIs from motor level control up to the highest level trajectory planning. And I've added some GIFs on the right side to give a sense of what it looks like. And we are also working on some upcoming features. We definitely want to add different types of gates, give the environment ground truth, occupancy, and then also along with that sign distance fields, which can be used in optimization-based planners, and finally event-based cameras, which are becoming more and more important every year in our field because of their high frame rate and asynchronicity. So most of our work is available in these two GitHub repos. We basically released AirSim Drone Racing Lab last week, which is like a cleaned up version of the repository of the Game of Thrones repository, which is listed below that. And there is, for more details, there is like an archive preprint available here, which was accepted in the PML proceedings for the competition track. Now I'm gonna move to the second half of the talk, and this is a research project we did with collaboration from Rogerio Bonatti, a PhD student from CMU, and my previous advisor Sebastian Scherer and Vibha from MSR. So here the premise is that like we want to focus on learning visual representations, which will help us an effective sim-to-real transfer of flight control policies. Specifically in this case, like we agree that AirSim is a photorealistic simulator, but still there is a lot of effort involved in recreating a test, like an actual realistic scenario, especially if you want to fly something in the real world. Yep. So the approach here is that, or the intuition here is that if we can sort of learn to extract features from the image which we think intuitively are meaningful for the task, and hopefully those features will sort of abstract away any of the useless or any of the domain gap between between simulation and reality. So in our particular case, we think like the visual information along with the relative gate pose of the gate, the relative pose of the gate from the drone is important. So this is what it's going to look at test time. You take an RGB image, you extract some latent space from it, you pass that latent space to a policy network, which essentially gives out a velocity command, which is passed to the flight controller. But at train time, what happens is like the way this VA is trained is you have two reconstruction losses, one for the image itself, and the other one is basically the relative pose of the gate. And then the policy loss is coming from essentially behavior cloning. So this is like the most basic imitation learning algorithm, and the expert planner is essentially coming from our move on spline API. So we basically generate a lot of randomized racetracks in the sim, log the commanded velocity commands used by move on spline to track that trajectory, and then essentially regress to those commands given the latent space. And this is just like a quick representation of what the latent space, the interpolation of the latent space. So we can actually constrain some of the latent variables to be meaningful, and by meaningful I mean specifically the relative spherical coordinates, for example here. So here you can see from this image to this image, we are sort of changing Z0 or R, which is mapping to R, and this gate is sort of moving it inside and outside the image. Similarly for relative roll pitching here. And these are like the other visual features. This little graphic is showing how we generated the training data. So here you can see move on spline in action. What's really happening is like every time I pass like gate n, I move gate n-1 to a random pose, so that like the training data set is still similar, but it's seeing different relative gates at every given time, and you sort of log out the commanded velocity commands. And then I'll quickly show some more real world results. So this paper was accepted at IRIS 2020. It's also available on arXiv. I think I've already talked about some of the things happening here, but here's like a top-down view of testing site at CMU essentially. And you can see these gates are quite professionally engineered. They are like swimming pool noodles and PVC pipes. And then we also tested them. We also ran the policy in some adversarial conditions, which is Pittsburgh most of the days of the year, heavy wind and snowfall. And then just to clarify things again, I think this is how the VA is trained. Your input image is RGB. You're sort of reconstructing. You have two losses: the image reconstruction loss as well as the relative gate pose at training time. But at test time, you basically just forward pass through the encoder. This is something I wanted to sort of highlight. So these are like images from the real world, input image A and B. So this is A, these are like, and then you're sort of interpolating the latent space vector between these two. So you can kind of see how this is interesting. It's really mapping approximately to the same pose and similar background variations along with the horizon line. And it's roughly changing smoothly across the latent space. And of course, we had some baselines. So from left to right, it's like increasing track difficulty in simulation. And then we can see, and then there's like an end-to-end baseline, which is basically training a sensory motor policy without any VAE or without learning any representation. And the last one is without the relative gate pose geometric loss. I probably skipped this in the interest of time. So yeah, this is like a nice visualization of the FPV image, the decoded image, and the decoded gate pose. So this is where the policy or the representation thinks the drone is. And here's another visualization of the real image, the decoded image, which is similar to the simulation domain. Looks like the AirSim image. And then on the left, we are basically accumulating the predicted gate pose. Of course, there's some error, but it's like roughly matching the real racing track. And some more results in the CMU swimming pool. So the code is available at this GitHub repo, AirSim drone racing VAE imitation, and you can also check out the paper for more details. Lastly, I want to highlight another project from pretty much ALA at CMU and Ashish at MSR. I'm not an author here, but basically they were using AirSim to generate So they basically collect a lot of varying environments in their lighting conditions, indoors, outdoors, for generating a data set for state estimation and like other autonomy tasks. And essentially what's happening is we are currently running a SLAM challenge based on this data set at a CVPR workshop. So you can follow this link for more details, or this GitHub repo for more details. And you can see there are like very varying conditions. And this data set in general comes with stereo images, disparity, segmentation map, along with LiDAR data, optical flow, and occupancy grids. So what I wanted to highlight here is that, like, if you open up their paper, they made some comparisons with the Kitty data set as to how aggressive and diverse the motion is. Because like in aerial vehicles, usually the state estimation problem tends to be much more harder. And they also compare it with the Europe map data set as well. And the way the synthetic trajectories are generated here is like you use the LiDAR sensor in AirSim, construct an occupancy map, then basically construct a roadmap from that in the free space, and then sample that roadmap to generate random paths. Once you have those random paths, you can again sort of generate ST3, like full trajectories and full poses, and basically make them easy, medium, or hard, as however, whatever is your preference. Yeah. Okay, so yeah, those were the 3-4 projects I wanted to highlight, and I'm happy to take questions at this point.
Thank you, Ratnesh. Can you hear me okay? Awesome. Can you do me a quick favor and stop sharing your screen?
Yep.
All right, so we're running out of time, but I'm going to cheat and give you 2 questions. Can we run AirSim in headless mode like Gazebo?
Yes, we can. I think it's documented in the GitHub repo.
Excellent. Good to know. There's one last question. What types of flying vehicles are supported by AirSim?
What types of flying vehicles are supported by AirSim?
Yep.
So, yeah, right now, I mean, we are like you can actually simulate any kind of multi-rotor you want, but it's relatively hard to do so, and we are working to make that easier. Out of the box, we Multicopters and other things in the near future.
Hello, mic check.
Yep.
Can you guys still hear me?
I can still hear you. Am I?
I get reports that audio is not working again.
Ouch.
All right, I think you're back. Let's do this right now. So why don't you join us on the PX4 Slack and the PX4 Dev Summit channel? There's at least 6 or 7 other questions from the community that are really cool. Why don't we try to do the interactive session there live if you're still available?
Yep, I can do that.
Sounds good. All right, thank you for your time, Ratnesh. I'm gonna hang up now and go to my live view. Thank you.
All right.
All right. Hey guys, welcome back to the PX4 Dev Summit. I have Ratnesh here with me, and thank you for the in-depth tour of AirSim. We really look forward to the open collaboration between PX4 community and the AirSim team. And by the way, Microsoft, thank you for being an awesome member of Dronecode and for sponsoring the PX4 Dev Summit. The effort by the Dronecode community is driving the open standards and is helping the open source community put the path forward for a lot of companies right now. And I think it's really important, everything that you guys are seeing here at the summit is just like a brief summary, a brief overview of everything that is going on right now. And I wish I had 24 hours of the day to stream but looks like my laptop is about to get fried and my camera as well. So let's do this. I'm going to introduce you to the next speaker, and towards the end of his session, I'm going to give him time for Q&A, and then I'll do some closing remarks with special announcement, and then I'll give the agenda for tomorrow. Guess what? It's packed with full sessions like today. Give me a moment while I look up James Howard from Iris Automation, and I'll be right back with you. Hey everyone, I'm back. Next up is the Beyond Visual Line of Sight feature of drone software and industry standardization by James Howard, founder of CTO of Iris Automation. And we're going back to San Francisco, California to connect with them. But before I connect you, how are you all doing? Are you tired? I am a little bit tired. I've been awake since a couple of hours now. I don't even have a sense of time. What time is it? I still have some energy for a few more sessions. Don't forget to ask questions on chat, join us on Slack, follow us on social media. You also want to quickly remind you that there's an after party scheduled for tomorrow, and that the link is only going out by Slack. So please join us. It's going to be fun. That's tomorrow at 3 p.m. Pacific. More details on Slack again. So let me connect you back to James in California. Give me one brief minute and he's all yours. James, can you do me a quick favor? Let's do a quick audio check.
Yep. Hello, test 1, 2, 3.
Awesome. I think I can hear you well. If I just get confirmation. And give me 1 second. I think we're good to go. How's everyone doing? Yes, we're good to go. All right, guys, this is the PX4 Dev Summit live from Tijuana. And next up, James Howard from Iris Automation, speaking about the Beyond Visual Line of Sight future and standards adoption. It's up to you, James. Thank you.
Thanks very much, Roman. And hi, everybody. I hope you're having a good time at the summit, and thank you for joining my presentation. Today, I'll be going over Beyond Visual Line of Sight and how we can get there through standards adoption. A bit of background on myself as we begin. I am the co-founder and VP engineering at Iris Automation. My background is in mechatronics engineering, space systems, and unmanned aircraft systems. At Iris Automation, we develop the Cassia system, which is an onboard detect and avoid technology that leverages computer vision and artificial intelligence to enable autonomy and increase safety within the airspace. Today, I'll be going over Beyond Visual Line of Sight and how that is achieved practically at the moment, as well as a discussion of the future of Beyond Visual Line of Sight drone operation, an overview of the standards that are being developed and released for UAS that are related to that, and where I see the PX4 and open source communities can continue their leadership in that space. Hopefully the outcomes today are an introduction to what regulators are thinking of when assessing Beyond Visual Line of Sight operation. Hopefully I can also spark some ideas for you or give you insights into how to operate drones beyond line of sight, and really kick off a conversation and collaboration amongst the open source community in enabling people who use the technology, the open source technology, to fly beyond line of sight. So a background on BVLOS, it's really the dream that everybody has had for drones from the very beginning. Thinking of the Jetsons and flying cars and package delivery fully autonomously is really where I think a lot of the industry wants to get to. And BVLOS operations for drones is really the first step to full autonomy within airspace, within the airspace and just aviation as a whole. Beyond Visual Line of Sight operation implies either no operator or a remote operator with very limited situational awareness about what is happening where the drone is flying, and that produces concerns from civil aviation authorities about airspace integration. Their job is to maintain and improve safety of the airspace, and so introduction of autonomous systems needs to be done in a careful manner so as not to impact that safety. As many of you are probably aware, BVLOS is fundamentally required for many different industries and applications, including search and rescue, scalable linear infrastructure inspection, package delivery, land and resource management, and urban air mobility, which is the fancy name for flying taxis. So to give you an idea of what the challenges are, well, the number one is safety, like I mentioned. And I wanted to share with you what this looks like from a practical perspective. So this is an image that was captured from a drone with our detect and avoid system on board. And you can see that we've made a detection of someone in the airspace around the drone and decided to take an avoidtive maneuver so as to keep that airspace user safe. And this is what it looks like zoomed in. what we came across was a paraglider. They're a very small aircraft. They entered the airspace completely unannounced. They have no radio, no ADS-B, no engine noise to cue a human operator, and they're flying at low altitude. And this is what governments and regulators are concerned about, is with the introduction of drones into the airspace, existing users like this could be severely impacted. And we want to prevent that from happening. So detect and avoid is one way there. And it's good to know that beyond visual line of sight is actually achievable. It's not completely walled off. We've seen in the United States an increase in approvals for 107.31 waivers, which is a waiver from the requirement for a visual observer, increasing over the recent years. And using the appropriate safety technology, BVLOS is achievable today. But as we'll talk about, the future will be a much smoother process through the adoption of standards. Currently, different countries have different processes, but the commonalities are operations within low to moderate risk airspace, using an onboard real-time detect and avoid system, and adopting a systems and operations approach to risk analysis, usually through the SORA process, the standardized operational risk assessment that was developed by JARIS. So the future of BVLOS is really to make this process a lot easier, make it a standardized process where standards for hardware, software systems, and procedures are adopted, and where the industry can move from permission to regulation. The difference in language there is that permissions are exceptions to an existing rule to allow you to do something outside of that rule, whereas a regulation would be a standardized rule set where if you meet the requirements of that regulation, you can operate without permission, just by default. And so the future of the industry is to move beyond visual line of sight to a standardized regulation where drones can freely operate within that regulation. And it's going to take a lot of industry cooperation to get there. Right now, many drones are built in a piecewise approach where many different components are sourced from many different vendors. And quite often the operator is the integrator. And there's a lot of overhead required under that paradigm for the integrator to do analysis and testing and verification to prove to the regulator that their system is safe for beyond visual line of sight operation. And so as standards are adopted and as systems are built, that becomes an easier process. So the future of beyond visual line of sight will require or include regulatory certification of complete drone systems, as well as subsystems to those drones. Ways that can be achieved are through the technical standards order process that exists today, as well as compliance and product testing for new standards that are being developed. And we'll talk about some of the ones coming out of ASTM in a moment, as well as type certification of unmanned aircraft systems, which is something that has really come about in the United States recently, and many companies are moving towards that. So at the end of the day, what it boils down to is that systems that meet standards receive a higher trust and face a simpler approval process from regulators around the world. And as we build more and more systems to standards, that trust builds and will set the future of where this industry goes. So the goal at the end of the day is a repeatable standards procedure to fly fully autonomous aircraft. A quick introduction to some of these standards. So who is defining them? Right now, at least in the United States, that is primarily ASTM and RTCA. Both organizations have had a history in the aviation industry for defining standards, and they have taken different approaches, where ASTM has focused primarily on small UAS and RTCA on larger UAS. And today we'll talk about ASTM. And just for background, in the United States and in many other countries around the world, a small UAS is one that is less than 55 pounds or 25 kilograms in mass. It's also worth noting some of the existing standards for aviation and avionics and where they fit in. So the common ones that are referenced are DO 178, 256, and 160. Currently, we're seeing that the need for those is really when people are on board the aircraft, and that they're not currently being applied to small UAS operating in low to moderate risk airspace, especially with the adoption of these newer standards that we'll talk about. And I guess lastly, how do we know what will be adopted and which standards matter? In our experience at Iris Automation, it comes from direct feedback from global regulators. We work with customers in the United States, Canada, across Europe, in South America, Australasia, and many other countries around the world. And we amalgamate a lot of feedback from these different regulators as they're assessing the programs that our customers are involved with. And that gives us insight into what's coming next. So looking at ASTM, we are expecting that the FAA is going to adopt in 2020 and 2021 two standards, both from ASTM. One is the UAS Software Dependability Standard, which covers a lot of software development procedures, test procedures, validation procedures, and a lot of organizational and process structures. The other is the Detect and Avoid Minimum Operating Performance Standard. And that's really what I'm going to focus on this talk, because it covers a lot more of the functionality of the drone and the safety and performance within the airspace. So a bit more technical as opposed to organizational. That standard covers the detect and avoid system, as well as its integration into the UAS system, which is the autopilot and the airframe and the performance of that aircraft. And it also covers the ground station integration, as well as human factors in remote operation using a detect and avoid system. So it's quite a holistic look at the full system beyond just the detect and avoid itself. It's how does that detect and avoid enable this drone to function autonomously and at the end of the day beyond visual line of sight. So it really touches PX4, Mavlink, and Q ground control, as well as Cassia, our detect and avoid system, and how they work together. So who is impacted at the end of the day? It comes down to the DAA, detect and avoid system manufacturer. So Iris Automation is one of such manufacturers, as well as the manufacturer of the UAS, the integrator of the UAS, and the operator of the UAS. And really the reasons to adopt this standard and to think ahead of where the regulators are in their requirements today is that by having technology that is compliant to a standard, it's enabling for everyone within the industry. Standards provide a simpler path for a customer or for an operator to go from procurement to operating beyond visual line of sight. And that really helps the entire industry grow and build trust between what we're developing today and the regulators who are approving its operation within airspace of their countries. The PX4 and open source can really lead in this regard. PX4, as well as other open source softwares, are already global leaders within the UAS market. And so we're already in a great position here where that leadership can be maintained into the future. I think that, as I mentioned at the beginning of this talk, that the different working groups and communities that are contributing to these pieces of software and to this technology need to begin starting or having conversations that include standards within those conversations. that it's more than the functionality of the software that needs to be assessed, but also how that software affects the end user and their application. And open source, to me, is really all about change and collaboration, and continuing that collaboration and continuing to work together collectively is going to be what's needed to make this shift towards standardization happen. So I'd like to see the community leverage the existing collaborative approach in the adoption of new standards. So Dronecode is a really good facilitator of that, especially between industry and open source. And the forums, of course, GitHub, Slack, the other different channels that open source has, or this community of open source contributors has, to continue that discussion and continue collaborating with one another and with industry who are implementing these pieces of software and technology into the airspace and working with the regulators directly. And like I mentioned, taking a systems level approach. So one example that I'll go into a minute is that a change to the ground control station could actually affect the compliance to a complete system, because these regulators around the world are taking a systems level approach to risk analysis. So they're not just looking at the autopilot or just looking at the drone airframe itself, but how that entire system works within their airspace. So looking at the ASTM detect and avoid minimum operating performance standards specifically, there are a few gaps within the Q ground control, PX4 and Mavlink that we have identified. And those are the requirement for continuous alerting for detected failures to the remote operator. So a temporary alert or a pop-up is not adequate to meet the requirements of the standard. It needs to persist until that failure is rectified. Additionally, adoption of Advisory Circular 25.1322-1, which is a bit of a mouthful, but in the United States anyway, it defines colors and terminology that should be used for alerts to a human operator of an aircraft. And currently, the alerts in Q ground control are a single color, always look the same. There are specific requirements in the United States for human factors interaction between avionics systems and the operator. Lastly, for Q ground control, the standard specifies that there must be visual awareness of any suppressed functions that could impact safety. So one of those is the auditory alerts that can be generated from alerts that come into the ground station, that text-to-speech engine. In PX4, the requirement for payloads such as detect and avoid systems to be able to talk directly to the ground control station via the command and control link is a requirement. And this is something that I think is functional in some cases, but not necessarily all. And then lastly, the standard defines geospatial alerts where the remote operator can essentially be shown where a potential collision might happen, as well as when that might happen, showing it on the map, showing it with velocity vectors of the intruders. Certain requirements like that are set out. That being said, the software has already been designed extremely well. Q ground control and PX4 follow great design standards, and there are many parts of the requirement that are already met by the systems today. So having alerts that are visual to the operator is required, something that pops up that shows the operator, hey, this thing is happening, as well as the requirement for active dismissal of those alerts so that they won't just go away after 5 seconds and the operator is left wondering what just happened, I missed that. The requirement to click the X button and actively dismiss that alert is already implemented. And then lastly, the text-to-speech engine already being implemented is another requirement as well. That's covered through the standard as well as the advisory circular for being able to notify an operator. Maybe they're not looking at the map at the time, maybe they're referencing their operating procedures manual, and they need that auditory input. And then in PX4 Autopilot, we see that the peripheral device heartbeat monitoring as well as fail-safe action already being implemented as a key part of that standard, where the aircraft itself is able to detect as well as react to potential failures of subsystems and safety systems that are required for that beyond visual line of sight operation. So the most important of those that is required from global regulators is the detect and avoid system. And then there are other systems as well, such as ADS-B or FLARM or UTM input that may be required under certain jurisdictions, and being able to detect failures of those subsystems is extremely important and already implemented within PX4. And then along with that, a generated alert to the ground control station about that failed peripheral. So we see that Q Ground Control PX4 already has quite a few of the features that these standards are starting to talk about and will be required in the future, and some new features and adjustments to the way things are done as examples for what this specific standard is talking about. So in summary, beyond visual line of sight today is really a stepping stone to what it will be in the future, where we are operating in a world where permission is required to operate beyond visual line of sight. And the goal and the eventual outcome is to see repeatable standard regulation so that beyond visual line of sight can be conducted by default if you meet the requirements of that regulation, in the same way that a pilot is able to go and fly their plane whenever they please because they meet the requirements of the existing regulation. And that's where we want to see the drone industry getting with beyond visual line of sight. And the way to get there is through standards adoption and building trust with the regulating bodies. And PX4 and open source communities can continue leading as they already have to date. And really, I'm excited to move on from this presentation and hopefully continue a conversation with myself and Iris Automation and other companies with the open source community and start building out the technology to meet the safety requirements and meet the input that the regulators are having and want to see from the community. So thank you very much for joining the talk. I hope this was a good overview of our little introduction to regulation. I think there's a lot more to say, and I want to continue that conversation now and into the future.
James, can you hear me?
I can.
Thank you. This is Ramon from Dronecode. Thanks for that awesome presentation. Wow, what a way to end the day. You're right. The standards adoption is the key across the industry, and we're glad that you touched on this point because that's what Dronecode is trying to do. And we want to invite everyone that is listening right now. If you want to join us and start talking about regulation and standards, this is the perfect time to do it. There's momentum. We're here, we're waiting, and there's no better time to do it than now. Thank you, James. If you would do us a favor, can you join us briefly on Slack? There's a few questions that would be awesome if you can join us there for a short Q&A session. Unfortunately, we're out of time on our live stream, but I really want to thank you and Iris Automation for all the effort that you did to be here today.
Yeah, thank you very much. I'm glad to be able to contribute and share our knowledge. And I will definitely move over to Slack now to answer some of those questions.
Sounds good. Talk to you soon, James.
Thanks. Bye.
All right. Wow. Okay, so let's do this. Since I'm technically a speaker and I need to do my closing remarks, let me load up the standby. Let's see if this works one last time. All right, so day one is almost gone. Lots of great speakers. Don't miss Paul Riceborough on his session premiering right now on YouTube. Well, not right now. I think in a couple of minutes. I think it's at 2:30 PDT. We've run into some production issues throughout the day. Thanks for understanding. This is what you get when you mess with live, right? This is the first time we're doing this. We feel very honored that we have you here. As you can see, the stream is just trying to end it right now. How are you doing? Are you feeling good? Did you learn anything today? Guess what I did? There's a lot of great information. I feel like I'm gonna need a whole week to process everything that we just discussed today. And we have a second day tomorrow. What? I want to thank everyone for joining us today. The more than 600 people that registered. Wow, that joined us throughout the day. 16,000 registrations. Thank you, community. Thanks for making this happen. Really excited for all of that. I hope your day was as enjoyable as mine. I feel like I was just chatting with friends and I had you next to me. I hope you had the same vibe. Definitely join us on chat next tomorrow. I will make sure that all those audio issues and video issues are fixed. I want to thank again Maxwell Innovations for joining us as a Dronecode Silver member. And I want to thank all of our sponsors, Autherian, NXP, Microsoft, 96 Boards, CUAV, Holivro, UBFi, and of course our beautiful partners, Demian San, Hackster, Open Robotics, and Innerdrone. Thank you guys for all of your amazing work. We couldn't have done it without you. And to all the 70 team members behind the screen, thank you again. You guys are doing awesome. Let's break a leg tomorrow. Thank you guys and talk to you soon. See you tomorrow. Bye.